James Tan, and I've been working with Unreal Engine 3 for the last 13 years. While I'm a programmer primarily, I've been using 3ds Max, Adobe Photoshop, and Unreal Editor for the last 10 years. I've worked on titles such as The Ball, The Haunted Hell's Reach, Cube, Epoch, and Ricochet. In this DVD, I discuss how to update your project to a new version of UDK, how to add pickups to Assault, how to add the announcer to Assault, an introduction to using Scaleform, an introduction to navigation meshes and waypoints, the various upgrades I did to the tasks system, an overview of AI and discussion over how it works, and integrating AI in Kismet. So it's been about 3 months since we last updated UDK, so I'm going to demonstrate how to update UDK to the latest revision. So normally what I do when I start up my projects is that I'll have the year and the month in the project folder. So this lets me know off the bat what sort of version that the project is currently on, and then I'll usually install the latest version in the same manner. So here we're transitioning from UDK December 2011 to UDK March 2012. So as you can see here, I've got SVN set up, and I would have done this right at the beginning of the project. So I'm going to make sure that the folder setup is at a similar state before I check out into this folder here. So I'm just going to put everything all here into trunk, like what I've got here. So I'll just set up the trunk directory, and I'll just copy these, or I'll move these into trunk. Okay, with that in place, I can probably check out this repository over to this folder here. Alright, so check out. There we go. And this is one of the really good reasons of why you should actually be using something like SVN, because it gives you a really nice and quick and easy way to transfer your files from, I guess, one build to the next build without having to figure out which files need and which files haven't changed and so on. So I click OK, and I export out. So it's adding all the files. Okay, so checkout is finished. So what we have here is a slightly different version of this repository, and that's because SVN will have tried to merge a couple of files, and these usually are text files such as configs. So what we'll do is we'll just need to double check the configs. So one thing we can do is we can go back there, and so okay, so it looks like the script files are different. But that's okay, these don't matter too much because we're going to recompile the scripts anyway. So we'll just jump into our configs, and we can see we've got a couple of differences here. So one of the nice things we can do is we can right click on there, SVN, and we can difference with the previous version, or difference here. And this allows us to see what's actually changed. And this is important because usually between each revision of UDK, Epic will add a couple of more things which is required by the newer versions of UDK. So, okay, so as we can see here, so this is the current copy, and we can see here that all of these lines were added. So we're going to keep those. So there isn't too much of a difference there, so that's fine. We'll have a look at usually this one here, default engine, changes quite a lot. So we'll just do a diff there. Okay, so one of the neat things, we can not only see the changes, but we can copy them across. So from there, we change that back. We can leave the transition map. We can leave the... Okay, so we can add that back in. Okay, so we can add this one back in as well. And we can copy that one back in. This is required for the front end cooker. And the same with this. And if we scroll down. Okay, so it looks like this version was the working version, which is March, has removed this line here. So we'll just leave that if it's not needed. Looks like Mobile Support has added these. Looks like March has added these things in. So we'll just leave them here there. And that's changed, but it's not a significant change. So we can leave that. And okay, so not a big change. So we can click on save and then it'll save our working copy. And we can close that. We'll have a look at default game and see what differences there are there. Okay, so we've changed these 3 lines. So we'll revert them back. And we'll change this line here. And that looks like all the changes. So we can save that. And we'll have a look at this change here. Okay, so it looks like this has gone from mobile input zone to UDK mobile input zone. Since we aren't using anything mobile, we can just leave all of that. And we can close that. And we'll have a look at this one here as well. Okay, so looks like UDK March has added 2 bindings, look up and look down. That doesn't matter to us. Alright, so they've added some bindings for the translocator and alt-fire on R, which is a bit odd, but that's okay, we'll just leave it. I see it used to be Q. And we want this one, because this one's relevant to Assault, so we'll paste that back in. And it looks like the editor has added 2 things, base path 0 and base path 1. We'll leave those. Okay, so the next thing we need to do is actually compile the scripts because they will have changed a little bit. Now, if we just run this, alright, if we just run that, you will see that it says that no scripts need recompiling. This is because UnrealScript compiler really only just checks the dates of the files compared to the packages. So if the packages have a later date, then it thinks that all the packages are up to date. We know this is not true, so an easy way to resolve this is simply to go into Assault Game. Let's just open this up in something like Notepad, and just do this to update the date. And what we can do from there is we can run that again. And as you can see, it's now forcing a recompile. Alright, so there hasn't been too much changes to the core UnrealScript code between UDK December and UDK March, so that's great. Alright, so the next thing we can do is we can update the SVN to ensure that we're not including any files that are random or anything like that. So we go back into trunk, we can do an SVN commit. Alright, so all of these have changed, and so have all the packages. So this is a new package, and this comes with UDK March, so we can just ignore that. But we want to include that, just in case that gets recompiled. So we can add a few comments. And it's usually always a good idea to add some comments as to what you did, so that as you go back, you can see exactly what's happened through the age of the project. So for example, if I do an svn show log on the development folder, you can see all the changes that I've made throughout the whole project, and I can go back and have a look at each thing. Okay, so the other thing we need to do from here is we need to have a look at the maps and make sure that they're still valid. So we'll just boot up the editor. Okay, so UDK has booted up. So we'll just load up our map to make sure that the content is still fine. So if there are any missing content or missing scripts or anything like that, usually when you load up a map, it'll bring up a dialog box saying, missing objects and so forth, like this. So we're missing some light cards. We're missing the UN light card slime. So as we can see, it's missing a whole bunch of textures there. So I know for a fact that DMDeck still exists inside UDK. So we'll just jump into there and see what text or what material those light cards are using. The light cards exist because they act as a sort of a way for Lightmass to know that things should glow. And it looks like that they were removed. So either we can re-add them in, or we can just remove them. In this case, I'm probably just going to remove them rather than recreate them. So we'll just see what mesh that is. Okay, so they're just using planes. So we can just select those. Okay, so we'll just delete those. There's some more here. And there's another set at another hole, which is over here. So we'll just delete those as well. Since these affected lighting, it's probably best to recompile the map. But from here, it's usually pretty good. So, alright, so after we do that, we double check our content. So a great way to do this, and this is particularly important, is if you've made some materials or any sort of content that refers to UT's content. Occasionally, when you download newer versions of UDK, some of the old content may be removed. So easy way to do that is, since we've got everything in a folder here, I can just right click on that and click fully load. And if that fully loads with no warnings, then we know that the content is fine. We'll also just save all the packages, as usually what happens in each UDK revision, when you save packages, it tags a new value into the package, and so packages know which version of UDK that they were made with. So that's all fine, so we can close that now. And after that we can recommit. And then that's it. So that's basically a really quick and easy way that you can update from an older version of UDK to a new version of UDK. We did get pretty lucky this time around in that there weren't many changes in those last 3 months. So it's usually a good idea to update every time a specific bug or a very specific sort of feature you want has been added, and it's and even then it's usually probably a good idea to update every couple of months. And this is really because if you're wanting to release a game soon, you probably want to just use the latest revision. So definitely a good idea. And this also highlights why you should be using something like SVN, is because SVN makes it really painless to update. You don't have to use SVN, but you can use something like Git as well, or Mercurial, or Perforce, which is a new option that's just recently opened up. So using a content management system like that really helps. And that's it. So in this chapter, we're going to have a talk about how to add some pickups. And pickups basically add a game mechanic to your game in that there are certain areas that become desirable to be in because they give something to the player. It can be ammo, it can be health, it can be new weapons, can be anything that you like, really. So Unreal Engine already provides us a pickup factory class, and this essentially is a waypoint in the map. And they were traditionally navigation points because this goes back to the days when Unreal Engine 3 was still using, and it still is using, waypoints such as path nodes and so forth. So it meant that it was known to the AI they could path to it and so forth. So we're just going to briefly look over this class and just sort of see what it's doing and how it works. So, okay, so we have a bunch of variables here. There's some stuff here that gets replicated. But we're going to actually detail exactly what it's doing. And to give you sort of a brief idea, is that a pickup factory is something on the map that just that level designers place, and they give something to the player. The pickup factory itself doesn't get destroyed. It goes into sort of like a hidden state, or a state where players can't pick anything up from. And then after some time, the thing that it gives out is respawned back into the map. So if you think something like health, when you run over it, it'll give you some health, but after some time, it'll respawn again. So these differ to things like the dropped pickups, and mostly in the sense that dropped pickups by themselves are usually things that are dropped by the player or dropped by an enemy that you've killed, and they generally don't respawn back in the same place that they were. So these, if we want to reference this back to something like Unreal Tournament, these would represent the things such as weapons that you can pick up, and then you can come back to them and they'll respawn, or double damage, and so on. Okay, so let's check out exactly what's happening. So in pre-begin play, and this is essentially called way before another event called begin play, and again before post-begin play. So whether you want to use pre-begin play or post-begin play or whatever else really depends on exactly when you want an actor to initialize. And basically in pre-begin play, you want this to initialize before most other actors are initialized. So this calls initialize pickup. So what we do here is the Unreal Engine will just check if there's an inventory type. So we then set a couple of these things here, sets the pickup mesh and so on. So we probably are going to override this since the things that we're giving are not always an inventory thing. We then have a set initial state, and basically this again is called by native code, and it just sets what state the actor should be in. Okay, and that's basically saying that if the inventory type is none, then it gets disabled. Otherwise, it goes waiting for match. Otherwise, it gets set to an initial state, or super, calls the super, and that does whatever else it needs to do. So, okay, so let's just check out the states and see if anything gets up there. We have an auto state. So by default, this is the state that the actor will be in, but set initial state can override this, you see. So, but anyway, let's assume that set initial state doesn't set to a different state. and it just goes into pickup. So we have a function here which is ready to pick up, and I imagine this is mostly used for things such as AI. So if they're scouting ahead, and if they need to know whether something can be picked up or not, they just sort of ask the pickup factory, can I pick you up, through this function here. We then have a valid touch function. So as we go through it, it just assumes that, it says that can the other pawn, just double checks that it doesn't equal to none. It can pick up inventory. It has a valid controller. It does a fast trace to ensure that there isn't a thin wall between the player and the pickup factory. And the reason why this check is needed is because normally with pickup factories, you normally just want to use something like a collision cylinder. And when the collision cylinder of the pawn and the collision cylinder of the pickup factory touches each other or overlaps each other, then sometimes this can occur if the collision radius is quite large, for example. And let's say, for example, there was a thin wall between them. So this check ensures that that you can't pick up items through really thin walls. And then we just double check whether the game allows the pawn to pick up this type of inventory. So there are a lot of hooks here that you can use. So on a global scale, you can use this to prevent pickups. For example, you can prevent all monsters from picking up weapons, but you allow them to pick up health, as an example. Okay, we then have this function here, function recheck valid touch. I think this is used as a timer. Yes, as you can see here. So if this touch here fails, and if it's because the other controller didn't exist, then we can recheck this. So just in case, yeah, as it says here, it's in the middle of spawning and so on and so on. So it just waits a certain amount of time and then just double checks that that the pawn can pick it up. And here we are. So touch is called when the collision cylinders or collision components of actors bump into this pickup factory. And this gets called. And as you can see here, we do a valid touch. And if it's valid, then we give something to the pawn. We also have a check touching here. And that's checked when the state is initially started. So this basically just is another way to ensure that if an actor was already touching it, but the touch event didn't get called, then this double checks to make sure that that those pawns are given the item. So okay, so let's assume that a valid pawn has touched the pickup factory. So what happens from here? So this function is called give2. So let's have a look at that function. Alright, so it essentially calls spawn copy for and then picked up by. So what does spawn copy for do? So it looks like it creates an inventory item classified or defined by inventory type, and that'll just be a class inventory type, so it's just a class. So it spawns that, and then it gives it to the pawn that that give2 was given. So this is a really simple way of, for example, a pickup factory can represent a weapon pickup. If a player runs over it, it then says, here is a new instance of this weapon, and it just gives it to the player. And then picked up by is then called. So what does this do? So it sets respawn. It triggers an event class. So this is for Kismet, and then essentially sets the anchor and so forth. And this is normally used for things such as AI, so that they can find their way through the navigation networks and so forth. But it's not so important for us. So really the big thing we need to check is, what does set respawn do? Okay, so it checks in the inventory type to find the respawn time. It then asks the world, the game, whether it should respawn or not. So again, this gives hooks to the game info to say, I only want this pickup to be picked up once. After it's been picked up, I don't want it to respawn. So it can override some defaults inside the inventory. But if the inventory can't be respawned, then it just goes to the disabled state. So this calls start sleeping. So what does start sleeping do? It just goes to the sleeping state. So let's check the sleeping state and see what that does. Okay, so we have a sleeping state. So it ignores touch, and that makes sense because the touch event doesn't need to be triggered when the pickup factory is no longer interested in that. We have a ready to pick up. So essentially this is used for AI, and if AI are able to predict when a pickup is going to appear, then maybe you want to set it a little bit earlier to say that's ready for pickup. So by the time the pawn reaches it, it'll already have spawned in. So we then have a begin state event call, and this event gets called when this state gets entered for the first time. So it sets the pickup to hidden, and that makes sense because you want the pickup mesh to be hidden when the pickup factory is no longer allowing players to pick it up. And then at the end of the state, so this event is called when this state is exited, it sets the pickup visible again. And again, makes sense. So these are statement blocks. So these are executed when the state is beginning. So respawn pause, so that sets to true. So if this delay respawn function returns true, it'll sleep for a second. And as you can see, the default implementation is that it's false. Eventually it goes respawns unpaused. So then we sleep. So basically when sleep is called, execution within the state block will stop for just a wee while, or as long as this value is inputted. So if, let's say, get respawn time was 3, then it might wait for 3 seconds or less, depending what the respawn effect time is. This can be 0 as well, and usually when it's 0, it just sort of waits until the next tick to do anything. Okay, we then, let's say that after it's done sleeping for, say, 3 seconds, it then goes down. It then respawns, it plays a respawn effect. So this can be like a kind of a sound or a particle effect. So we'll just have a look at that function, see what that's doing. And it's been stubbed out. So normally you want to create your own one. So it then sleeps for a little bit of time. So this allows you to play back an effect, and then to maybe the weapon grows larger, or maybe the weapon reses in, or something like that. So then it goes back to the pickup state. So then pickups can be picked up again. So this is where these two are handy. When the state first enters, we hide the mesh. When the state is exited through this method here, it then makes the mesh visible again. So let's have a look at these two functions and see what they do. As we can see here, B pickup hidden is true. We then hide the mesh. So you would have noticed that these are simulated. So there doesn't seem to be any replication here. So how exactly are clients knowing that the pickup factory has actually changed? And the way it does this is probably using this variable here, because bForceNet update is set to true. This essentially tells the network that all clients should be updating this actor now. So we'll have a look at B pickup hidden. So as we can see here, B pickup hidden, it's got rep notify, so we're going to find it being used inside replicated event, well, more than likely. So as we go down here in the replication, we've got here bnet dirty. So when this value differs between the server and the clients, the server should send it to the client. And we've got here replicated event. As you can see, B pickup hidden. When that has finished replicating, it will call replicate event with the var name as itself. And if B pickup hidden is true, this is now on the client, it'll call set pickup hidden. But if it's false, it'll call set pickup visible. And so this is one way of synchronizing between the server and the client. So we've sort of already discussed exactly how pickup factories work. So initially they are in a pickup state, a player runs over it, it's then determined as a valid pawn to run over, so it gives the pickup, it then goes into sort of a sleeping state, it sleeps for a while, and then it exits out and goes back into the pickup state. And this is the simulation between the pickup factories on the server and the client is mostly maintained just through the visual means, because in reality, most of this code here, such as the touch events and so forth, don't really need to be run on the client. Sorry. So the client doesn't really need to determine if a point has touched the pickup, because the server can determine that, and it just sends the result as a boolean, which in this case is B pickup hidden. Okay, so let's have a look at the assault pickup factory, and let's have a look at what we've done here. So in the assault pickup factory, we know a couple of things. We know that it can give health, we know that it can give ammo, and we know that we have two other ones that give double damage to the player and a berserk mode to the player. So let's have a look, and as you can see, we've got classes for each one of those. So let's have a look at the base assault pickup factory and what I've done there. So the first thing I've done is I know sort of exactly what the things are going to look like. I know they're going to have a static mesh at the bottom and then a static mesh in the middle that sort of floats upwards and downwards. And I know I want them to be lit. I know that I want to have a little glow with them. And since I know that they're not going to give inventory items to players at all, I want to do some checks too. I want to change some of the checks to the inventory type variable that was defined inside pickup factory. So the first thing I do is in the post begin play, I grab the default pickup static mesh translation, and basically this grabs the vector out, and this allows the level designers to place that floating mesh in a slightly different Z. And I need to grab that value out because I'm going to animate that. And that becomes more clear a little bit later on. I then here have initialized pickup factory. And you may have wondered why I've stubbed it but haven't done anything with it. And this is more than likely. This is going to be because I don't need the functionality inside the superclass. So that's fine. And that's the same with set initial state. I've done the same thing here. I only call the super navigation point set initial state. And that's because I don't need the previous implementation of pickup factory, but I do want the implementation of set initial state inside navigation point and its parent classes. So this is really useful if you are subclassing a particular class and you want to call the super function of its parent class, but you don't want to call its super function. So let's say you have a parent class A, B, and C. You want C to call A, but not B. You can use this sort of construction. Okay. We have a set pickup mesh, and this does this. And again, I've stubbed out spawn copy form because I don't need to use inventory type. I have a give to here, and I don't need to really call spawn copy form, so I haven't done that. I've only just got pickup. I've got a get respawn time, and this returns the respawn time. Now I've stubbed it out like this, just in case subclasses want to modify that for any particular reason. I don't think that happened, but I've just done it as a just in case. It's there so that in the future, if I want to extend the system, I can reasonably easily. I then have a simulated tick function, and this essentially simulates the actual turning and the floating of the actual pickup. If I jump into UDK, you'll know exactly what it means. So here we have a pickup. So if I run over there, you sort of see how that health mesh is floating upwards and downwards, and it's also rotating as well. So this is done through the tick function. So let's examine that. So basically, pickup static mesh dot set rotation. So I'm setting its rotation of not the whole actor, but just of the static mesh inside the actor. I grab the previous rotation value, and then I append it with the pickup static mesh rotation rate times the delta time. So the reason why I multiply that by the delta time is because the delta time gives me the amount of time that has passed since the last update, and this is given to me through the tick. And because of that, if the frame rate goes down, then the delta times are going to be longer because more time has passed since the last update. And so this ensures that the rotation rate of the static mesh is time-based. And so it's always going to be smooth, and if it's choppy, inside the frame, if the frame rate is choppy, then it'll move slightly faster as well. So this maintains that smoothness. We then do a pickup static mesh set translation, and this makes it bob up and down. I can also make it do something else. And again, I use the default pickup static mesh translation because I don't want to lose that value. I then add with a vector that's pointing straight up and down. I multiply that by the sine of the world time, and this basically generates a value between -1 and 1, depending on the value of the time. And since we know time is always incrementing, that's going to produce a nice sine curve for us. And then I multiply that by the pickup static mesh floating height. Since I know this is a value between -1 and 1, it's going to produce a sine curve, and the sine curve height is going to be based on this value here. And the reason why we need to multiply this with this vector here is because this is a vector, so we need to add them together. Okay, so that's how we do the animation. We then have some other functions here. We've then overridden the pickup state, and that's because I just need to insert another thing into valid touch. And I've got here can pickup, and basically can pickup is always true, but this essentially allows me later on for the different pickups to evaluate whether or not they should be given to the player or not. I've overridden the sleeping state, and I've essentially just made it a bit more simplified because I didn't need all that stuff where you could delay a respawn and that sort of thing. So then I create all the components that I need. So the light environment, the draw light radius and draw light radius component, and so on. And this is for the point light, and that's because I want the pickups to actually have some sort of a light value to them. I then have all the static meshes, and I set some default properties just so that if the level designer doesn't want to override these, then at least there will be some sensible values there to begin with. It's generally a good idea to have some sensible default values, and this essentially allows you to, when a game designer creates an archetype of your actor, at least, you know, when the game designer puts that actor into the level or into the map or anything like that, at least, you know, the archetype is going to work. If not exactly what the game designer intended, it'll at least do something. And in my experience, as long as it does something, then the game designer will automatically think, oh, okay, it's working, but the variables are wrong. Whereas if you had no variables, or whether, you know, if the respawn time was 0 and if the rotation rate was, say, 0 and so on, then it would appear that the actor does nothing, and that would be more likely thought of as a bug. Okay, so when we check here, we notice that this is abstract, so we can't archetype this. And the reason why I've made it abstract is because even though it has a lot of the base functionality, or it extends the base functionality from Pickup Factory as well, is that I don't actually want anybody to make archetypes of this class. And that's because on its own, it still doesn't do anything just yet. So making an archetype of this class doesn't do anything. So let's move a little forward, and let's move over to the Assault Pickup Factory Health, and let's see exactly how that works. So we've got here, and it extends Assault Pickup Factory. I've got a variable here, health to give the human. And the reason why I have this is because the health pickup in the Assault game type can actually detect the difference between the two different pawns that pick it up. So if a human picked up this Pickup Factory, then it will give him health, equivalent to this value here. Otherwise, if it's a cyborg that picked it up, then it will regenerate some shields. It will start the shield regeneration for the cyborg. So I have this function here, can pickup. And again, this was used to determine whether or not, if a pawn runs over a Pickup Factory, whether or not it's considered to be valid or not. And essentially here what I'm checking against is that if it's a human pawn, then I basically check, you know, has the human been damaged? If it has been damaged, then return true. If it hasn't been damaged, then it goes down, and it goes down here and returns false. So a human with full health, when he runs over the health pickup, isn't going to pick it up. And I do the same thing for the pawn. for the cyborg, and I essentially just check, if it's a cyborg, you know, if it has less shields than its maximum shields, then it should return true as well. As in that, if a cyborg has been damaged and its shields are lower, then when it runs over a health pickup, it'll pick it up. Okay, so we then implement the give_to function, and rather than giving an inventory item, we make it do something. So in this case, if the pawn is a human, we check that by typecasting. We then heal the pawn based on that. And if it's a cyborg, we then call start shield regeneration. So normally with pickups, there isn't a lot of things you need to worry about when it comes to the network and replication. Most of the time, the server evaluates everything, and the clients don't need to simulate that. They just need to represent the results. So in this case, because the cyborg has already been set up for replication of its shields and so forth, we basically need to just say on the server, hey, start your shield regeneration, and the shields will be regenerating on the server, and since the shield values are passed down to the client, that'll just replicate fine. So let's just check out this function here, start shield regeneration. So as you can see, with start shield regeneration, all we do is we clear the timer. This timer here is basically the delay of when a cyborg gets hit. There'll be a short delay before shield's regenerated, and it just starts the shield regeneration timer straight away. Plays a sound and just starts healing the shields. So, and because this assault pickup factory is not abstract, we can archetype this, and we can do various things with that. So we'll just jump into UDK, and we'll just see exactly how you would set up an archetype for this. Alright, so in UED, we can make a new archetype. The easiest way to make an archetype for actors in this case is probably just to drag and drop it. So, okay, so there it is. It's even bold, so that means we can place it. So we drag and drop. And as you can see, it's added a light because we have a light, but there's no appearance. There's nothing there. So if I press F4, it'll bring up a bunch of properties. And with the properties, I can expand them. So by default, I'm giving 25 health to the player. Maybe I want to give 10. So maybe I can make a variation of this health pickup to give, say, 10 health to the human. I can then adjust a whole bunch of things. So I can adjust the base static mesh, and that represents the base of the health pickup. So if I scroll down and have a look at some of the UT stuff, maybe I'll find something nice that's applicable there. So here we go. This is nice. So I want to make sure it aligns to the floor, so I'll just check the collision height. So as you can see, the collision, even though the location is in the center, the collision height extends out from there. So if I just check the collision, what's the collision value? It's 80. So if I set the translation of this thing here, -80, there we go. I have a glow stick mesh, and that basically represents sort of like a glowy thing, and this is basically this thing here. So I can assign that there. As you can see, it's there. I'll just align it. So okay, so the pickup mesh. So what do we want to use to represent the floaty thing and the spinny thing? So in this case, since we're giving a little bit of less health, I'm just going to use this one here. So we do that. And again, it's way up there. So I'm going to push it down a little bit so that it's not so far away. Something like -30 will probably do. There we go. And maybe I want to make it a little bit bigger. So 1.25. Okay, that's nice. And maybe we'll just change the light as well. So okay. So as you can see, everybody can do this. A programmer sets up the initial thing, and then a game designer comes in and sets up how it looks like, and maybe then the artist comes in and just sort of ensures that everything's located in the right place and so forth. So respawn time can stay at 5. rotation rate can stay the same, and the state mesh floating height can stay the same. So if you want to check exactly how that's going to behave inside the game, we can just click start. There's that guy there, and as you can see, it's all set up, it's all going. The thing is rotating, the thing is floating upwards and downwards. Okay, so how do we transition from what we have here into an archetype? Now, with the new release of UDK, and even with older versions of UDK, once you have an actor set up, you can actually just right-click it and click on Create Archetype. This brings up a new dialog box, and then you can say, my package, small health, and click OK. And that will give you an archetype with these parameters here. So in the first DVD, I showed you one way of doing it, which was to go into the actor classes and then to right-click Create Archetype. But this is another way of doing it, and it's usually a nicer workflow. So, and one of the cool things you can do is that if you modify this archetype, now, because this is an actor based on an existing archetype, if you modify this, it won't change the original archetype. So you can create variations of one archetype inside a level. Now, let's say I wanted it to give 15 health, but I wanted all pickups to give 15 health. You will have noticed this will have changed because this is now bold to tell you that it's changed from the original archetype. But if you want to modify the archetype, you don't have to necessarily open this up and then change it to 15. You can also just right-click and you can say Update Archetype from this instance. And once you do that, double-click that, you will notice that value is now 15 as well. So that's a really handy way of doing it. Another new feature with UDK March is you can now create child archetypes. And what this basically means is, let's say I right-click this, I can create a sub-archetype, which is, again, another name for a child archetype. I can say the same package, so my package. And I can say large health. So this archetype here is based on this archetype. So what do I mean by that? So it means that if I drag and drop this, you'll see it's very similar, or it's in fact exactly the same. I can change something in there. So I will change the static mesh, since it's a large health pickup. Oops. Right. Okay. Now, just because now that I've changed something, if I were to change the pickup mesh on static mesh on that, this won't change because I've changed it in a future revision, which is this child archetype. However, if I change something in the base which hasn't been changed inside the child archetype, it will replicate over. So, for example, I want the draw scale of all of my health archetypes to be slightly larger. So I can just set that, and since I haven't changed that value inside the sub archetype, it'll replicate across all of them. And this is a really nice feature because it allows you to make a base archetype and then you can create sub archetypes off of that, and it basically makes the workflow much, much easier. However, I don't want to keep that, so I'm just going to revert that back to 1. The only downside with that is that you can't have a sub archetype that is of a different class. I mean, that is kind of nonsense anyway. But other than that, it's a really nice feature. So the last thing I'm going to show you with archetypes is that's really useful for pickups is because the names themselves don't always help, especially when you start having a lot of archetypes. For example, in the Assault game, I have quite a fair number of archetypes now, like that, and all you see is like a sea of red icons, basically. So one of the nice things you can do is you can actually load up, you can actually assign an image. So here's all my base archetypes for all the different things. So one thing I can do, let's say I wanted to assign an image to this. I can take a screenshot of the viewport and it will assign it to here. So if I position my viewport so it encompasses that reasonably well, I can right click the Berserk pickup and I can say capture thumbnail from active viewport. And there we have. So as you can see, you've got a nice sort of an image, and you can keep updating it, repositioning it, so that you get a clearer idea of exactly what this archetype represents. So as you make more and more archetypes, if you don't want to see an ocean of red icons in your content browser, then spending a little bit of time to update the icons here can make it much, much easier for your artists and so forth. So okay, we got a little bit off track there, but we'll now jump to the rest of the pickups. So let's have a look at the ammo pickup. Okay, so again, the ammo pickup extends from Assault Pickup Factory. We then have a bunch of, we then have an array of valid weapon archetypes that we can give ammo to. And then we then also allow the level designer to specify how much ammo to add. We have we extend the can pickup function, and basically we're just ensuring that the weapon, the pawn that runs over the pickup has a weapon that's valid. So it just scans through the valid weapon archetypes, and it just checks the pawn's inventory actors to make sure that they have an archetype that matches. If we find a hit, we then check if that weapon actually needs ammo. So let's say that inside the valid weapon archetypes, we have a reference to the link gun archetype. We iterate through the pawn's inventory actors. We then check, is your archetype or is your inventory item, does it have an archetype that's the same as the link gun archetype? If yes, then do you actually need ammo? So that returns true. And then we do a give to. So essentially through here, we scan through the valid weapon archetypes. We then grab the inventory that has the same object archetype as the valid weapon archetypes. We do two things. First, we start the ammo regeneration, and we give some ammo. And if we check out those functions, it's quite simple. So as you can see here, add ammo. So all it does is that it grabs the last ammo count. We do an ammo count, and then it returns how much ammo is actually added. So this can be useful sometimes if you allow partial pickups, for example. Let's say you have an ammo pickup that gives out a maximum of, say, 50 bullets. And if your gun only has 25 bullets that it needs to fill up, then it can take 25 out and it can leave the pickup with another 25, for example. So, there are some options that you can do. So again, that's kind of a nice simple function. If we go start ammo regeneration, all I do here is I clear the timer, ammo regeneration timer. Basically, that timer just keeps track of when the player shot something. There is like a little brief amount of time that has to pass before ammo regeneration starts. So I just clear that timer, and I start the ammo regeneration timer. So, pretty simple, really. And that's all I need to do. And again, to set up a pickup factory ammo, I do it in exactly the same way. I go to the actor classes. I find the class question. I can then just drag and drop, and they'll set up an empty one for me, and then I can customize it, and then I can create an archetype from there. Okay, let's have a look at the double damage. Oh, and before I jump onto that, so the assault pickup ammo, all of the archetypes have already been set up inside a package. So if you check out the assault game engine assault game _ engine, and if you just look into the pickups, you'll notice that there is a bunch of archetypes that I've already created for you. So if we look at the link ammo pickup, you can see that the valid archetype is the link gun, gives you 25 ammo, and so on and so on. Okay, so the double damage. So double damage is a little bit more complex because we're not giving the player anything. We're not giving the player more ammo or health in this case. We're giving the player a sort of a state that they can be in. So how do we do this? So the first thing is that, well, we specify a double damage time. So this is how long double damage lasts for. Again, we override give to, and essentially we don't need a can pickup because anybody can pick it up. So all we do from here is we typecast the pawn that picked it up into an assault pawn, and we amplify damage. So what does this amplified damage function do? And it takes, and you pass the amplified damage function the double damage time. So what does that do? So right, so we set the damage multiplier equals to 2. We then set a timer down here. If the timer is already existing, then we append on the time. So basically, if your double damage pickup gives you 3 seconds, if the player already has a second, it'll make sure it increments that up to 4. And when the amplified damage timer is eventually called, it resets damage multiplier back to 1. So what does damage multiplier do? So since we know it's related to the weapon, we can see what that does. Right, so we have this function here called getDamageBoost, and we can see that it takes into account if the pawn has amplified damage, and we also use the damage boost value. And this was the damage boost value was used back in DVD number 2. So where is this function being used to get damage boost? So we can see here that it's being used inside the projectile fire mode. When the projectile is spawned and fired, it grabs the damage boost. And same with the trace as well. So it's kind of a nice and simple way to do damage boosting. And again, replication is not really necessary unless you want to replicate the state. But again, it's not too much trouble because really what you're doing here is since most of the damage calculations is done on the server, then it sort of automatically replicates down to the client, since take damage and health and shields and so forth is automatically replicated down. Okay. So finally we look at the Berserk one. And the Berserk is a similar thing to the double damage. Again here we don't extend can pick up because everybody can pick it up. We typecast into the assault pawn, and we say enter Berserk mode. Okay, so enter Berserk mode. Right, and we basically have a very similar thing. We increase the firing multiplier rate. It multiplies it up by 30%. And let's see where firing multiplier rate is actually being used. Right, so it's being used here. So basically, when the get fire interval is being calculated, as in when a weapon is fired, there is a small timer that gets run, and while this timer is being run, you can't fire again. So essentially, we're just reducing that time. So basically, all Berserk mode does, it makes you shoot real fast. Okay. So that's about it for the pickups. And so that's how I went about adding all the pickups. Very simple. Just an actor. We didn't really have to worry a lot about replication because most of what it affects has already been replicated. So for example, ammo is already maintained in the weapon, so I'm just adding ammo. Things like shields and health, that's already being replicated, and things like damage is being calculated mostly on the server. Firing rate is also mostly calculated on the server as well. So most of it's already been kind of set up for you. So just quickly, something I wanted to append on is the one thing I did forget with the replication is that the amplify damage and the berserk mode actually adds a counter on the HUD. Now I forgot to sync this with the client. So essentially, since we know that enter berserk mode is called from the server because the pawn on the server touches the pickup factory on the server, it then tells the pawn on the server to enter berserk mode. Now we know this is running on the server, so we can do something like this if role equals role authority. This basically just double checks if it's running on the server as such. We then call client enter berserk mode. Now this is a remote procedural call basically. So we're sending a replication packet down to the client to call this function. And I have here reliable client function, client enter berserk mode. Now it sends the berserk time as well, so of how long the berserk mode should last for. So, and basically we just call enter berserk mode. So this just synchronizes with the client to also enter berserk mode as well. So on the client side, they'll manage and set up their own timers so that the HUD can display that it's in berserk mode. And I've done the same thing for the amplified damage as well. And again, I didn't need to do anything else other than that, because yeah, damage is set up mostly by the server, and same as the firing rate. Although in this case the firing rate is also simulated on the client, so it actually benefits us to have this timer here, so we can use the same types of checks as well. So okay, so the very, very last thing I need to do is probably just mention about the HUD. And because I've already mentioned that when you pick up double damage and when you pick up the berserk mode, you actually get a counter. So if you came from DVD number 2, you'll actually be able to see probably how I've done this. And it's set up in pretty much in exactly the same sort of way. Okay, so let's just check where that's being set up. Right, so that's been set up inside the assault pawn render stats. So I've set up inside the assault pawn because there's really no need for the HUD to go back and ask the pawn, do you have amplified damage or do you have berserk mode on? Because since the pawn already receives a call to render something on the HUD, I just thought, well, we just do it in here. So in this case, I have some properties inside the HUD properties that represent the berserk and double damage. Now these are stored inside archetypes, and you have to remember that you have to actually set these values inside the archetype, otherwise nothing gets rendered onto the screen. You also have to set some values for the berserk U, V, UL, and VL. Otherwise no image gets drawn as well. So with that out of the way, as you can see here, I do something very similar. So I calculate the remaining time for the double damage. So, which is over here. Calculate the remaining time. I convert that into text and I just draw that onto the HUD. And then I draw the icon in the same sort of way. I really discussed a lot about the canvas and the HUD inside DVD2. And even from there, the UDN and the web has a lot of tutorials that sort of really talk about the HUD. But if you're wondering exactly how I got the counters and the icons onto the HUD, it's inside Assault Pawn. Okay, and that pretty much wraps it up for the Assault pickups. Okay, so the next thing we're going to add is adding an announcer which can provide some feedback and also reward the players when they've done something cool or correct or something along those lines. So the way we normally do this is we normally just calculate on the server some sort of metric or record on the server some sort of metric to keep track of what the players are doing. And then when the time comes, we just play a sound. So the way that I've set it up inside the Assault game is I've used two classes. One is a properties class, and one is an announcer object. And basically, both of these are just objects that just contain some data and contain some functions. So in the case of the Assault announcer properties, it's just a way for me to reference all of the sounds here. So I've got one for the bullseye, which is 5 kills in a row with a link gun. Combo King, which is 5 kills in a row with a shock rifle combo. The dominating sound kill, this is the 15 kills without dying. A double kill, 2 kills in 5 seconds, and so on. So I'll just demonstrate how you create this archetype, just for those of you who missed it in DVD 1. So after you've made this class here and you've compiled the package, you can then jump into the actor classes. You usually have to turn all of these off, because in this case, we're making an archetype of an object, and if this is checked, then only actors will be visible, like so. So you don't actually see that. Rather than trying to scroll through and go through this list, because there are a lot of stuff here, you can simply type in announcer, and that'll just filter everything out. So then we have here is Assault announcer properties. So you can right click on that and create archetype. And you can create that in any of the packages or a new package inside a new group and give it a new name. So I've already done this for you, and it lives inside the Assault game _engine package. So if I click on there, I've got the announcer properties here. So if I double click on that, I've filled out all of the properties with sound cues. So we haven't really talked much about the sound cues and how you actually make them and what the properties do. So let's go a little bit into that. So one of the things with the original sounds inside UT was that for the announcers, they only came as these WAV files. So they exist inside UT3 sounds int, which is the localized folder. And you have here announcer reward. So they're just sound node waves, and normally you can't just sort of play these back very easily. So it's much easier to play back a sound cue. So what exactly is a sound cue? So a sound cue is sort of a bit like a little mini script as such that sound designers can create themselves, and they can add various properties. So let's have a look here, and you'll see that I've made a whole bunch of sounds here, or sound cues here. And basically, if we were to open these up, they're very simple script, like this. But let's actually look at some of the features. So we'll make a new sound cue. So the quickest way to make a sound cue is to right click and new sound cue, sorry. And then you can type in the name of the one that you want. So it brings up like this, and this is basically the end result. So this is the mixed result. So if you need a sound which attenuates based on distance, you would add a node for that. So it's very similar to using something like Kismet or even the material editor. So you right click and you have the attenuation. So this allows you to set up various properties such as how it fades out over distance, whether it's linear or logarithmic, and so forth and so on. You can also add a delay, and delays are useful for various reasons. So say, for example, you want to mix in a sound. So if we grab two sounds, like so, and we'll just look up sound. So you may have a sound like this, which you may want to play immediately. And then after that's done, you may want to play that sound. Right. So how do we mix these two? So we can use another sound cue node called a mixer. As you can see, it has two inputs there. So we can connect that up to there, and like this. So when the script plays back, it goes through the mixer, so it knows it has to mix two sounds together. So it plays this one first because there's no delay. And then after this has been processed, this delay, it will then play this. So we can set the delay to about the length of that, which is 0.13. And if we play that back, you'll hear the two sounds one after the other. So using the sound cue editor allows you to make sort of new sounds by mixing old ones and the waves together and so forth to create different things. So say for example you wanted to do a thunder, and initially thunders have a sort of a rumble, and then they'll have sort of the strike sound. So you can play the rumble first, and then you can have a delay, and then you put in the strike sound. And you can even add other ones, like you can have a randomizer which selects between different ones. So like so. So doing things like this just sort of frees up a lot of the time that programmers have to spend to come up with different ways sounds should be played or things like that. So if you need to, for example, in the old Unreal Engine 2, if you wanted to randomize between lots of different sounds, you had to create an array for that, and then you had to play the sound that was randomized within the array. But with Unreal Engine 3, you can make a new sound cue, you can use the randomizer node, you can put in as many sound samples as you wanted, and then from that, the programmer just says play the sound cue, and it will automatically play a random sound. You can also put delays in, as I've done here, and you've got some other options too, such as a modulator, so you can slightly vary the pitch so that it doesn't always sound exactly the same. So we can add this a little bit after all of these, for example. So as you can see, as you can listen, the sounds are played back slightly differently. So this is a really powerful tool for controlling sound. And I guess, unfortunately, a lot of people don't tend to use this as much as they should. They tend to rely on a lot of Unreal scripting. But it's getting a little bit out of the scope of this chapter, but you can create a lot of cool stuff using the sound cue editor. So anyway, let's have a look at the sounds for the announcer. So as you can see here, when I double click on these, I can play them back. And since they're announcer sounds, I don't really need to add a lot of things. I don't really need to add attenuation. I could add modulation so that the sounds, that sounds slightly different each time. But in this case, most of the time, they're just simply the sound node wave connected up to the output. So, like so. And that's because I don't want any effects. So you will have noticed what are these things inside the square brackets. If you look at the other sound cues inside UT, you will have noticed that there are different things as well. And basically these are sound groups, or sound classes, I should say, is the proper terminology. And with sound classes, it allows you to filter out between different types of sounds. So you can classify some sound cues as music, and you can classify some as sound effects, and so on and so on. And this allows programmers to adjust the volumes of each individual group and to add special effects to each individual group. So say for example you were making a game where you had grenades, and when a grenade exploded nearby you, you'd sort of get this ringing sound in your ears, and different sound effects would sort of be muffled out, or volume would go down on those. But you don't want the music to change, and so you can stick a couple of sound classes to be modified when the grenade explodes, but you don't modify the music sound class. So if I show you how the sound classes have been set up, it'll suddenly make a whole lot more sense. Right, so in this package here called Sound Classes and Modes, there are a bunch of sound classes that have been created beforehand. And if we look at the sound mode, if we just double click on that, you can see here it's got a bunch of EQ settings that you can set. There's a bunch of sound class effects that you can add, for example, the sound class name. You can adjust the volume and the pitch. You can apply to children. And this will make more sense when you actually have a look at the tree structure. So let's jump into this tree structure, the master tree. So it's usually called master. There we are. So, as you can see here, these are all the sound classes, and these are all the ones that you can set sound cues to. So, even with music, you've got 3 different ones. Even with voice, you've got dialogue, chatter, movie voice, option voice, and so on. So, basically, if you adjust the volume of this one, it'll act as the master volume control for these 3 here as well. So, this is why sound effects has been split up into so many little different ones, because this allows the sound designer to explicitly just reduce the volume of, say, weapons, vehicles, and items and characters, but leave these other ones alone. Or, if the sound designer wants to, they can adjust the sound effects, and it will adjust all of the children as well, if the sound mode dictates to do that. So, for the low pass, for example, sound class effect, if I want to adjust this SFX, which will adjust all of the children down here, I would have to click Apply to Children. Then that would adjust the volumes of everything down the line. So the one thing that you have to remember, if you tweak any of these things, you have to use this package here. You can't rename the package, you can't use a different package, so you just have to modify this package here. Okay, so let's examine, now that we know exactly how the sound cues work and a quick overview of the toolset and that sort of thing, let's examine exactly how the code is actually picking up sort of when players do something in order to play back the announcer sounds and so forth. So if we go back to the assault announcer class, you can see that this is an abstract object class, so it can't be instanced. But what we have here is a static final function. And we have a function here called play announcement. Now this function here, basically when you call it statically, you pass it a sound cue, you pass it a team index. If the team index is equal to 255, or if you don't supply a parameter, then it defaults to 255, then it basically plays it to everybody. But if you set a team index of say 0 to 1, then you can play messages just for the blue team or just for the red team. So because this is a static function, we can grab the world info statically using the get world info, and this allows us to iterate through all of the player controllers. Once we iterate through all the player controllers, we can tell them each individually to play back a sound using this function here. Now, the reason why we have to do it this way is because when you replicate functions, they only replicate to one client. There isn't an automatic way to broadcast to all clients, and this is the reason why this sort of function exists, is so that when we want to make a single call to replicate a function to all clients or to selective clients, which in the case we've done with team index, then we need to set up in this sort of way where you iterate through each individual client version. So in this case, we're iterating through each individual player controller and then sending the replicated function call through that way. So say, for example, if you wanted to replicate a function to all pawns, you could iterate through all of the pawns on the server side and then call a replicated function. So that's one of the major differences between a replicated function and a replicated variable. Replicated variables are sent to all clients, whereas replicated functions are only sent to one client. So this allows you to create the simulation where a single client, for example, can see something or hear something or do something that other clients can't do or can't see or can't hear. Okay, so this doesn't go into much detail of how we actually detect the actual events. So since most of the actual events revolve around the players killing someone or doing something like that, as we can see here, everything is to do with kills. The most obvious way to detect that is actually inside the game info. So the game info actually has some hooks that are called when a player kills another player. And this function is usually called score kill or killed, something along those lines. So if we look inside the original game info, can see here, this is the original function here. It's a very simple one. It just increments the deaths for the killed player. We call the score kill function. We discard the inventory for the killed, and so on and so on. So we subclass this inside our assault game info because we want to do some extra stuff. We call the super, so we retain the original functionality. Now, we can announce the first blood sound here. So we have a boolean here which says has announced first blood. So basically we don't want to keep saying first blood all the time. So we just have a simple boolean which is false at the beginning of the game and then is later set true when it has been announced. We then also check that the killer controller is not the same as the killed player. So a player can't jump into lava or kill themselves and get the first blood. So if a different killer has killed another player, then we then say that, okay, we then grab the announcer properties first blood sound cue, and we can do this because if we look inside the assault announcer, we'll notice that the default properties for announcer properties is referencing the one that we have in our package. And so because of that, we can pull the values out directly. So we grab the first blood sound cue and we send it to the player controller that actually did the killing. So only the player that actually did the killing will receive the first blood sound. If we wanted to send this to all players, then we could use the static function here. We could use class assault announcer dot static dot that, and we could play that sound there. So, and that's if we wanted to announce to all players. But we're not going to do that. We only want to send it to the player that did the killing. Okay, so that's first blood taken care of. How do we actually handle the rest of them? So the way that I've decided to do it is inside the player replication info. So, and that's really because the player replication info already keeps track of a whole ton of other stuff, such as how many kills has happened, whether the player has died, and all that sort of thing. So, so what we do here, we have a notify kill, which is called inside killed anyway. And I just forward that to the killer's player replication info. So if we look inside the player replication info, we have a couple of variables here that's related to the announcer, such as kill streak, combo king streak, and rocket scientist streak counter, and so on. So if we look at the notify kill, so okay. So first of all, we check if it was this player that was killed. And if this was the player that was killed, we basically just reset all the stats. Because once he's been killed, he won't have a kill streak anymore, and so on. And just actually looking at this function, this actual thing will never be parsed. And the reason why that is because I'm only grabbing the player replication info from the killer. So let's actually fix that mistake. So we also want to tell the killed player to also receive the notification. So we grab that out as well. Okay, so both the killer and the killed, both their player replication infos will now receive the notify killed event. So this will actually be entered. Okay, so if the player was killed, then all of his kill streaks and so forth, they all get resetted. And same as this timer here with the multi-kill timer. And I'll go into more detail very, very soon. So, okay. So for the player that was the killer, first thing we do is we grab the player controller, we grab the kill streak, we increase the kill streak, sorry, and basically increasing the kill streak is used for things such as double kills, multi-kill, monster kill, and so forth. So we then check the damage types, because that's being received in here. So if the damage type was shot combo, then we increase the combo king streak. But we set the rocket scientist and the bullseye to 0. And that's because we want those particular reward announcers to be played, if you got 5 of those in a row or 3 of those in a row, for example. And we do the same thing with the rocket. We increase the rocket scientist, but we set the others to 0 and the link plasma. So this is sort of a nice mechanic which encourages players to stick to a single class for a certain amount of time rather than switching between them all the time. So if the kill streak was equal to 1, so if this was the first kill, then we start up the multi-kill timer. And we give the player about 5 seconds. So as the player continues to keep killing and killing and killing within 5 seconds, then this gets activated more and more and more. And so if, say for example, if he gets another kill, and the kill streak is now equal to 2, if the timer is active, then we can announce the double kill. And then if he gets a kill streak 3, we announce the multi-kill, and so on and so on. So this is a nice way to just let the timers do most of the tracking for us. So in order to get, say, the monster kill, players have to kill 6 people within 5 seconds. So just by doing it this way, it makes it nice and simple. So otherwise, we also then check the combo king streaks as well, and the rocket scientist and the bullseye streak. And finally, if none of that was valid, we then check for the kill streaks over a longer period of time. So, for example, if you killed 5 people over, say, 30 seconds, then you may want to reward the player. So, but if the player killed somebody and then died, you probably want to reset that, which is what we've done up here. So over a period of time, if the player continues to keep fragging other people and doesn't die, then they get some announcements such as killing spree, rampage, and dominating, and so on and so on. So this is a pretty simple way of implementing announcers. You can also add some other sort of triggers for announcers as well. So maybe if you're doing a capture the flag sort of game, maybe when the flag gets captured, you could use something like this static function here to announce to everybody that the blue flag or the red flag has been captured. Let's say, for example, in the assault game, if you had some announcers for saying, to go get the bomb, you could use this function here again to announce to the red team to go grab the bomb, and maybe to announce to the blue team to defend the bomb or something like that. So adding announcers is a fairly simple task. It's a little bit of work on the replication side of things, as we've shown here. It's not that much. But most of the work actually comes from detecting when the events occur and then just responding to those events. Okay, so we're going to have a look at the implementation of a scoreboard into the assault game. But instead of using the canvas, we're going to actually have a look at Scaleform. So what are the major pros and cons of using something like Scaleform versus, say, using the HUD? Well, from a start off, is that with the canvas, you have to write a lot of UnrealScript to get things onto the HUD. And we could see that with things such as rendering health, shields for the cyborg, and ammo for the guns, and so on. And usually, in terms of a HUD design, as a programmer, design is not really your forte. That's just the reality. So by using something like Scaleform, we really we give the designers an advantage because they can use a tool such as Adobe Flash Professional to make the HUD or to make the GUI and so forth and do all the design work in there rather than have to sort of convey that design to a programmer. And that's a really big pro. So if you haven't heard already, Scaleform allows Flash movies to be played within UDK. So in the same principle that we as programmers allow designers to use archetypes as a way to create new weapons and to create new behaviors and so forth, Scaleform allows Flash designers to make up and to create the HUD and other types of menus within the game. Another really big pro is that not only are the tools done, but things like animation is much, much easier. So Flash is already designed with animation in mind. So, and because of that, doing things such as tweening and rotating and moving this and that and then fading this in and out, just doing that inside something like Adobe Flash Professional is much, much easier than getting a programmer to do it. Because for a programmer, they can create a customized tool set to do this in UnrealScript, but it's really not something that you really want to be sort of spending your time on, especially when it comes to creating a UI. So having a tool set that's already there and that's already designed to do this sort of thing is another big pro. Another big pro is the fact that you can also delegate some of the functionality of the menus to inside ActionScript. So the latest version of UDK now has Scaleform 4, and that in itself supports ActionScript 3, which is much faster than ActionScript 2. However, both are still usable. And being able to delegate some of the functionality of the UI into ActionScript is really useful from the perspective of allowing the Flash designer to create some interactions using ActionScript without having to sort of try to, mix in UnrealScript into the animation. So say, for example, you wanted to have a mouse cursor and little particles of fire could spawn out from that cursor. Now, you could use UnrealScript to create all the particles and to simulate them. However, being able to do that inside ActionScript is just easier, and besides, the designer gets to decide exactly how he wants those to interact with everything else. So some of the potential cons of using something like Scaleform is that if you're not used to using the Flash toolset, then it can feel like there's a bit of a time delay because you have to learn how to use the tools. So that's one thing. So as a programmer, if you want to get like a really simple menu up and running, having to learn Adobe Flash Professional might seem like a daunting task. So that's one possible con, and it really depends on your team size. The other potential con is that even though we now have the benefit of using something like ActionScript to delegate away some of that functionality into ActionScript, it can be really confusing if you don't document your process really, really well. So say, for example, 6 months ago, somebody made a function inside ActionScript 3, and it just happens to do something automatically. And then when it comes to 6 months to now, if you're wondering how that functionality is implemented, you have to go through all of the UnrealScript, then you have to go through all of the ActionScript till you finally find it, and then you realize, okay, so that's what's happening. So you have to increase your documentation processes. Another potential con is potentially you can write ActionScript which can be exceedingly slow. So both ActionScript 2 and ActionScript 3 are interpreted languages, which means that the commands and so forth aren't compiled. You basically just write it and something will interpret the language and it'll just run stuff and execute things accordingly. So because of this, it's actually slower than UnrealScript, and so you still have to be reasonably careful not to have too many complicated things or too many complicated logic inside your ActionScript. So if there is a lot of stuff going on, it can be important to actually shuffle some of that code into UnrealScript, so it does the calculations there and then forwards it to ActionScript. So sometimes those sorts of things can also sort of hang you up when it comes to using Scaleform. Other than that, those are really sort of the pros and cons I can come up with right now. So let's dive into the scoreboard and let's have a look how that actually functions. So let's actually bring up the example of what the assault scoreboard looks like. So the scoreboard is bound to F1. So as you can see there, when I hold down F1, it brings up a nice little animation, and then it sort of fills out, and then it goes to display all the stats. And then if I let go of F1, it animates away and fades away. So it's this animation process and fading away and so forth that is really the nice part about using something like Scaleform. Okay, so let's have a look at the associated classes of how we actually bring something like that up. So every single bit of Scaleform is an asset which sits inside a package. So the Scaleform in UDK works by importing the Flash files themselves, or the Swift files themselves, into Unreal Engine. So I won't go over too much detail about how exactly that's done, because I'm using an existing scoreboard inside UT3, but there are plenty of tutorials out there which sort of discuss exactly how to go through the basics of importing in a Swift file and so on. So as you can see here, we've got all these textures, and we have all these Swift movies, and that these are all imported from a directory into a package. So to play back a Swift movie, we use a base class called GFX Movie Player, and this essentially just plays back a Swift movie, and it has a bunch of functions and variables that we can access and use to be able to control how the movie plays back. So for example, if you wanted to simulate a situation where you can click on a button and it jumps to a different frame of the movie, you can use some functions there. If you want to grab some of the symbol instances and so forth, you would use the functions there. So the first thing is that the Assault scoreboard extends from GFX Movie Player. We have a bunch of structs here, and I'll explain all of these as we proceed down into and sort of actually use these. We then have a reference to a whole bunch of GFX objects. So a GFX object is an UnrealScript representation of things like an instance of a movie clip, or an instance of an image, and so on and so on. So a lot of the times, if you were to think of the whole thing like a tree, you would have one root object which has everything in it, and then you might have, in this case, a scoreboard and an overlay and then titles, and they can be stacked inside each other. So being able to pull out these references so that we can use them straight away without having to dig through the tree makes it nicer to work with. And you'll see exactly how we work with these. So it's a reasonably complex scoreboard. You know, there are a lot of objects here. We then use these structs that we've defined above here. And again, I'll go into more detail with those a little bit later. Okay, so before we jump more into the scoreboard class, let's actually discuss how on earth, what actually causes the button the F1 button, when you press it, to actually bring up the menu, and then when you let go of F1, it releases it. So how does that actually work? So that's actually triggered from inside the HUD. So what I have here is a reference to the scoreboard here. And if we just search for where that's being used, so we have precalc values here, so it's being used inside here. Essentially, precalc values, this function gets called when the resolution of the game gets changed. And since we need to rescale the Scaleform movie, essentially what we do here is we record a boolean to check whether or not the scoreboard is open. We then close the scoreboard movie, and then we re-instance the movie. So that's basically a real simple way to rescale it. Here in the post-render call, you can see that we tick the scoreboard movie. Essentially, we send the render delta, which is a very similar concept to delta time. Render delta basically keeps track of when the frame was rendered minus the last time the frame was rendered. So yeah, we get a delta time value, and that just forwards the tick. And I'll explain, and we'll go more into that function a little bit later on. We have two functions here called onCloseAnimComplete and onOpenAnimComplete. So these are used for the scoreboard, and we'll go into more detail that soon. And this function is also used by scoreboard, and again, we'll go into more detail that soon. So we have a exec function, set show scores, and a boolean. So as you recall, exec functions are they become console functions that you can call directly from either the console or from a keybind. And if we were to actually look into the keybinds, you can see that the button F1 is bind to a command called GBA show scores, and if we see what that function does, or see what that keybind does, you can see that on press, it calls set show scores and it sets that to true, and then when the button is released, it calls set show scores and it sets that to false. So that's basically how it is. When you press the F1 button, it opens up the scoreboard, you let go of it, it then removes the scoreboard. Okay, so when the button is pressed, this function will be called, and this will be true. So it'll go into this block here. So we check if the scoreboard movie is none, and if it's none, we instance a new one. So the reason why we have to use new instead of spawn here is because GFX movie player is not an actor, it's an object. So you have to use new. We set the local player owner index, and this basically is a reference to who actually owns the movie. And as you can see, it's referenced here. So who owns the movie? We then set the timing mode. And again here, it sets the timing mode of the movie to either advance with game time, respecting game pause and time dilation, or real time. So if you're using something like a HUD and you only want it to animate and blink, you want it to respect pausing. But if you're using something like if you're using Scaleform for a main menu, you probably don't really need to pause when the game is being paused and so forth. So we then set the external interface. So basically the external interface points to another actor where ActionScript can call functions. So here we are. Object that should receive external interface calls from interface. If it's unspecified, thus is none, then external interface calls will be routed through to the movie player itself. So this thing is actually used to control these two functions here. So essentially when the scoreboard opens, when the scoreboard animation has finished, it'll call this function here. And then when the scoreboard closes, or when the scoreboard has finished animating its close animation, it'll then call this. So these are some of the default functions that you'll find inside sort of that Flash movie. So if you have Flash Adobe Professional, you can find it inside the UDK folder. Flash, and if you go to UDK HUD, you have the UDK scoreboard.fla. You can open that up and you could sort of find the call to these two functions inside the ActionScript. So for now, just really know that they're there and they're being called by ActionScript. So once we've instanced that and set up these parameters, we can then check if the movie has been opened. And if it hasn't been opened, we start it up and we play the open animation. So let's have a look at those two functions. Actually, before we move on to looking at those functions, if this was false, then it goes down to here, and all we see here is scoreboardmovie.play close animation. When the animation has finished, it'll call scoreboardmovie.close. So we close it, but we keep it in memory so that we don't have to re-instance it again later on. Okay, so start is called, and we call the super of that function. So that might be a native function. Yes, it is. So it's a native function, and basically it just starts playing the movie. And we advance to frame 0 or time 0. So basically we just initialize all the objects in the first frame, and we don't actually advance the movie at all. So it's just a way for us to initialize the whole thing so that we can actually start grabbing all the objects out. So if B initialized is false, so that's just a variable that we use to keep track of whether the movie has been initialized or not, just in case we call start multiple times. We then configure the scoreboard, and then after that we draw it. So okay, so what does configuring the scoreboard do? Configure scoreboard. Okay, so the first thing we do is we grab the root movie clip. So for those of you who know ActionScript, you'll know that _root is sort of an object variable that always exists inside Flash. And then everything else inside it and all the instances are usually contained inside that root movie clip. So we grab the main scoreboard, and again we use the reference to the root movie clip. We've already checked that it's not none, so this won't get an access none. and we can grab the object. Now all of these functions are inside GFX object, as you can see here, get object and so on. We then set some values, underscore x scale, underscore y scale, and so on. These are just sort of default or sort of variables that just always exist inside all movie clips. We know there are actually two modes to the scoreboard. The scoreboard was made by Epic, so the scoreboard has a bunch of modes. It can be in just DM mode, where it only shows the results of one player, or it can be inside TDM with just team deathmatch. Since it's sold as always team, we just set it to that. So basically this is go to and stop to a certain frame somewhere within the movie called TDM. From there we grab the overlay. So basically in configure scoreboard, we're just grabbing all of the Scaleform objects. So this is sort of to initialize. So once you've grabbed all the objects, we can do other stuff with them. Okay, so we set up the red team, set up blue team, and again, set up blue team and set up red team is essentially the same sort of code where we're just basically grabbing all the movie clips out from Scaleform so we can use them inside UnrealScript. Okay, so after that, after we've grabbed all these values out, what happens from there? Okay, so this then gets called draw. So what does that do? Okay, so the draw function grabs the player controller. Now the player controller that's grabbed is the one that owns this movie. So this is the reason why we had to set this right at the beginning. Now since we've grabbed all of these movie clips, such as title TF inside the configure scoreboard, they'll all be here. So we can adjust these. We then update the headers. So what does that actually do? So update headers. So it updates the red team's score, blue team's score, and the remaining time. So if we see that again, so what the header is updating is the game text, and it's just set to game at the moment because the default game name inside the game info doesn't actually have a value. It's just called game. And then it sets the remaining time, which is the score on the upper right hand corner. And then it sets the red team score and the blue team score, which is both currently 0. Okay, so what does this draw function do? So update previous state. Okay, so this basically stores the current game state. So we grab the remaining time, the red score and the blue score. And we have here remaining time, red score, blue score. So this is the scoreboard state. The reason why we want to do this is because we don't really want to be updating Scaleform every single tick and every single time. Not only is this wasteful to update, but it actually is quite expensive to do that as well. If you send Scaleform updates every single tick when it's not required, all that's happening is you're just wasting CPU cycles. So by keeping the previous state, we can keep track of whether or not we actually need to update the Scaleform or not. So for example, since we know that the game name doesn't ever change, we can probably cache that once and then just upload it to Scaleform just once. Things like the time, we know that changes every second, but usually ticks are, 1/60th of a second, for example. So we only need to change that, every 60 ticks or so. So it's a good idea to really make sure that the updates are done on an event basis rather than just blindly doing it every single tick. Right, so after the initial Scaleform scoreboard has been set up inside draw, how do we continue to update this? Because this is in a loop. So, and this is where the post-render tick is important. But before we go to there, I just have to mention that the scoreboard movie, after the start has been called, it then calls play open animation. And play open animation basically just tells the title, the footer, and the overlay to play an animation starting at the frame called open. So in post-render, if the scoreboard, it checks if the scoreboard movie is none, and if the scoreboard movie is open, then it just simulates a tick, so it forwards a tick. And inside the tick, we do a very similar thing. We grab the player controller that owns the Scaleform. We then update the PRI list, so this is a new one, but we continue to update these two as well. So let's have a look at update PRI lists. So update PRI lists is done in the same fashion as the previous scoreboard state. Basically, this is the reason why we have the earlier structs. These keep track of the players and their current states, such as player names, scores, and deaths, and so on. And essentially, we cache it inside UnrealScript first. And if UnrealScript detects a change, we then forward those values to Scaleform. And again, this is to reduce how many times we actually need to update the Scaleform. So, as you can see here, we iterate through the player replication info arrays. So we grab each player. We then test to see what team they're on. If they're on the red team, or if they're not on any team, then we update one of the rows defined by the red score rows. And the red score rows array has been filled out by the setup blue team function. As we can see here, blue team. The blue score rows has been set up there, and the red score rows has been set up there. Otherwise, if the player is on the blue team, we then update the blue team row. So the reason why we keep track of the player count is because in this particular scoreboard, there is a set number of player entries in the scoreboard. So, and there's only 12 of them per side. So we just make sure that we don't go over that. The second thing we do is we check if the player replication info is for the local player. And the reason why we want to do that is because we want to change the rendering of the player's entry to something slightly different. So if it is, we do a set player row and we update the footer. So we'll just look at set player row. So you can see that for the player row, we increase its Z, so it just brings it up a little bit. Now, the great thing about Scaleform is that it's actually 3D. So you can tilt and you can rotate the Scaleform movie, and if they have different Z values, they'll appear above other things as well. So that's kind of nice. So the next thing we do is we get the object called item G inside. We don't need to cache everything, so sometimes we can just get it. It is expensive, but since we don't set the player row often, we just do it like this. We then go to and stop to a particular frame called default. For the player, we set to go to and stop to player. So we're switching the frames inside that movie clip. So if we examine that, so if I add a few bots, like so, and if we press F1, you can see how my player has been highlighted. So if I change the name, you can see how I'm been highlighted. So that's essentially what this function is doing here. And so that's a really nice and easy way for designers to simply say that for this particular entry, I want it to look different. So they make another animation frame inside Scaleform, and then when we set it up inside UnrealScript, we can just jump around to the different frames to represent different states. So after that's been called, we call update footer. So what does this do? So this one here essentially just sort of puts the player rank, either coming first or second. We then update the player placement, the scores, and the names, and so forth. So at the bottom, we see the player's name and so forth. So if we just do that again, we can see that when we press F1, it updates this my placement, which is number 2. It updates the name to James, and the score and deaths are both set to 0. Okay. Alright, so from here, the other reason why we keep the red player count and the blue player count is because as players leave, the PRI array shrinks. Now we want to clear those entries out, obviously. So one thing we do is, if the number of red players has reduced, then basically all the rows after that, after the number of red players, we just clear every single row. So that's why this one exists. Such as here. So in the clear row function, all it's doing here is setting its opacity or its alpha back to 50, and we just clear all the text for scores, deaths, and name. So one of the nice things, as you can see here, we've actually got this parameter called HTML text. So Scaleform text fields, which you place inside Adobe Flash Professional, actually allows HTML. So this means that you can colorize text, you can apply styles, and all of those sorts of fancy things to text fields, which is also very handy if you're trying to do chat style systems and things like that, which again is reasonably difficult to do inside just Canvas, for example. And now we'll actually get to the meat of the Scaleform class, and that's inside this function here called update rows. So inside the update row function, this basically checks if the current and the cached version of the score info matches or not. And if they don't match, then we need to update the Flash UI. So the first thing we do is we check whether or not the player name for this player has changed with the score entry. And if the score entry was, initially set to player name is just a null string, then it basically indicates that this hasn't been used at all. So we really need to refresh everything. So we set the opacity up to 100 to make it less transparent. We update the score, we update the deaths, and we update the player name. So, and again, we just bypass this. So if the name hasn't changed, we then check, has the score changed? If the deaths hasn't checked, we then check, has the deaths changed? And each time, if anything has changed, we set this bUpdate item renderer to true. And at the end, if bUpdate item renderer is true, we then send those changes over to Scaleform. So that's actually really the meat of how the scoreboard changes its score and deaths and updates the player names and so forth. We've already seen how it clears away players that have already left the game as well. So the last thing that we can really touch upon is how to go from UnrealScript to ActionScript. We've seen how to go from ActionScript to UnrealScript using external interface. One of the nice things you can use is functions called ActionScript void. And it basically allows you to call a ActionScript function which returns nothing, which hence void. There are other versions of this inside GFX object. So you can grab, an integer from a ActionScript method, or a float, or a string, or an object, and so on and so on. And in this case, we're calling a function inside ActionScript called update after state change. So in this case, ActionScript may decide to realign some things, or may decide to colorize some things, things like that you sort of leave your designer to do. Whatever they want to do, they can just do it without having to modify UnrealScript. So that's really a quick introduction to something like Scaleform and how you would add those in. And hopefully this helps you to sort of explore Scaleform as a viable option for menus and things like that. As of UDK February, Scaleform is now supported inside iOS. So if you're making an iOS game, it's still applicable there. And that really covers it for the Scaleform introduction. Alright, so one of the first things that we really need to talk about when it comes to AI is navigation. How do they find their way through a level? And there are two primary methods, two methods of navigation in Unreal Engine. There is one method called path nodes or waypoints, and the other method is called the navigation mesh. Now, waypoints and path nodes or path nodes have been around for a long, long time. They've been in there since Unreal Engine 1. And essentially, the way that they work is you place path nodes around the level, like so. And what these path nodes represent is locations in a map that the AI can go to. And when you place them down, you'll notice this icon comes up. And basically what it's saying is that the paths need to be rebuilt. Now, what happens when you rebuild paths? Essentially for path nodes, they do lots and lots of traces in between each other, and they calculate whether or not a path node can reach another path node. And this forms like a really basic grid. So as I place more of these down to represent different areas of the map, alright, so when we rebuild the paths, okay, so paths have been rebuilt, so what actually happened? Well, we don't see any reach specs. The reason why you don't see any reach specs is because you actually need to, one, you need to select the actors. So we need to select all the path nodes. So now that they're selected, we then press P on the keyboard, and there we see all the actual reach specs. Now the reach specs are color-coded. Quite hard to see. I'll just change it so that, there we go. So as you can see, we don't have any reach specs between this path node and this path node here, and that's because you can't see. Well, they can't see each other because there's a box here that's blocking the pathway in between those, and same with this and this. And so if the AI was, so say the AI is here, and he wants to reach down there. Now the AI is first going to do a check to see whether he can reach there directly. So they'll do a trace, and the trace will return while this thing is in the way. So the next thing that the AI does is that it looks into the waypoints and it says, find me a path in which I can travel along in order to get to the point that I want. So what the pathing will do, actually I'll just change the material on that so that's clear. Nope. Right. Okay. So what the pathfinding will do is that it'll go, okay, this is the nearest node to the pawn, and it'll then find the nearest node to the exit point to the final destination that you want the AI to go to, and then it says, okay, find me a path between these two, and it uses an algorithm either A star or Dijkstra's, and it basically finds a path that goes, if you want to get to that final destination, you go to this path node, then you go to this path node, then you go to this path node, and then you go to this path node. Now, it may not choose those exactly because I'm just sort of looking at it, but it may decide that this is actually a shorter path to go there. But that's sort of the basic theory of waypoints. So it's a very simple theory, and it's a very simple system to use as well. You basically just put path nodes all over the map. You ensure that when you ensure that when you have finished placing down all your path nodes, you click on the build paths, and you just double check by selecting all of the path nodes and then pressing P that there are basically the spider-like web thing everywhere in the map. So these reach spec lines actually have meanings. As you can see, this is green, and it's documented on the UDN as to what these colors actually mean. And usually, colors like white, they typically mean that it's a path that they can use, and it's wide and so forth. They're not going to collide into anything. And green, I think, means that it's slightly narrow because there's something that might block it. Just things like that. So now that we've talked about path nodes or waypoints, we can talk about navigation meshes. So I'll make a new map. So there are two types of navigation meshes. Well, in reality, what I mean is that there are two types of ways to generate a navigation mesh. One of them is the original Unreal way of doing it, and the other way is using an open source library called Recast. And we'll cover them both and sort of the pros and cons. So to build a navigation mesh, the first thing you need to do is you need to place down a pylon. And a pylon indicates an area in which to build a navigation mesh. And a pylon is also found in the drop-down menu, Add Actor. It's just slightly off the screen, so I'll just bring it up. Add pylon. And you get this funny looking symbol here. And if we switch to top view, you'll see this light blue box. This indicates the bounds of which to generate the the navigation mesh. So for example, if I put it there, the limits are going to be all the colliding space, which is here. This is all empty space, so it's not going to generate a nav mesh there. And it will generate up to these bounds here. So if I click on that, you can see it's generated a navigation mesh, and it's respected the bounds. So since we want to cover the whole map, we're going to move it to about there. And we're going to need to expand the box out a little bit, because if I was to put the pylon inside the cube, it's going to generate the navigation mesh inside that cube, or on top of the cube, which is not the desired effect that we want. So we just make it a little bigger, like this. And then if we click on Rebuild Paths, you can see it's generated for the whole lot. Now, what is the actual differences between the concepts between a navigation mesh and a waypoint? Immediately that you can see is that waypoints represent a point in the map, whereas a navigation mesh represents an area. And the major difference is that waypoints only tell you a small amount of information about the level in terms of pathing. It gives you a very strict grid of waypoints that the AI can follow in order to get somewhere. Now, a waypoint doesn't tell you much information in terms of, is this a really wide corridor or is this a narrow corridor? It doesn't give you any information about the overall area. And that's really the biggest gain that you get from shifting to a navigation mesh. So say, for example, we had the waypoint system. And if we overlay this on top of this, remember, if you wanted to get from here to there, the AI didn't really have a lot of choice in how it wanted to go there. And it had to say, okay, well, I have to follow this path node, this path node, this path node, this path node, and then finally go to there. With a navigation mesh, because it has a true concept and has a true understanding of space, there are several things it can do. One is that if you have radically different sized things, so if you had, say, a massive tank, it could also use the same navigation mesh because it knows the actual area, it knows that it can fit within around the edge there. Whereas with a waypoint, because it doesn't have a true concept of space, it may have to use a second subset of path nodes which are more intended for vehicles or just things like that. And that's really where the power of the nav mesh comes from. Now, the other power of the nav mesh is that it lowers memory use. For example, if we wanted to detail this space here, as you could see before, we placed down quite a few path nodes, and then it generated all the reach specs in between them. So there are probably more path nodes than there are the number of polygons in this navigation mesh. There are also more reach specs, which details the information between waypoints. There is more data being stored there, and so overall, more data is being used to represent less information. And the other really good thing about navigation meshes is that it's really quick to generate. I don't really have to worry too much about where I place the pylons as such, but it just sort of, I click a button and it generates the whole thing. Whereas for path nodes, I have to be very careful. I have to place them, here, here, and here, and here, and I have to tweak those around to try to find the best path possible, and so on. And path nodes are not really adaptive to change. Once you have a level and you place down path nodes, if you decide to change the level, you'll have to readjust all your path nodes again. Whereas with something like a pylon, or with a navigation mesh, sorry, I can duplicate this box, for example. I can do this several times, and then I can hit the rebuild, and it creates a new navigation mesh with respect to those new boxes that have been placed down. So as of the latest version of UDK, UDK March, there is a new method of generating navigation meshes, and it's called Raycast, or uses an open source library called Raycast. So how do we enable this? We enable this by double-clicking on the pylon to open up the properties, and you have this option here which just says use Raycast. So if we click on that, then Unreal Engine will use the Raycast library to generate the nav mesh instead of its own internal one. So we then click on that, and as you can see here, it's now regenerated that navigation mesh using Raycast. So there are some obvious wins here. So if we put these side by side, and if we set this one to not use Raycast, and we rebuild geometry, and we rebuild paths, you can see that the actual results of the navigation meshes are actually different. For a start, there tends to be more polygons in the older version. There is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So in this case, there was actually more polygons generated with this simple map. The polygons generated by Raycast tend to be cleaner. They tend to be bigger as well. Whereas the ones generated by the original navigation mesh system tend to produce really thin slivers and so forth. The other big win with the newer system is that it's really fast. So for example, if I switch to a much larger map, something like this, right, so with the map loaded, if I place down a pylon, and then if I hit that, it takes quite a while to actually build. Right. So as you can see, this is really what I was talking about. In a realistic map, or in a real map, the older method tends to generate a lot of real tiny slivers, such as these. Generate some really odd things around curvatures like this. And so on. So especially here, you can see that you've got some really reasonably messy sort of navigation mesh being generated here, and so on. So if we switch that to Raycast, it's also they're basically just benefits when you switch to Raycast. One, it's faster to generate the navigation mesh. It's cleaner. It's usually more simple geometry, and because the navigation mesh is producing paths out of the polygons, having simpler polygons basically means that pathing is going to be faster. It's probably going to be more accurate, and so on. So just double click on that. We select that and we click that. So as you can see, it's really fast, and it tends to generate much nicer polygons. As you can see here, we don't have the weird sort of polygons being generated up here. We don't tend to have these tiny, tiny slivers. So you get reasonably nice, interesting, big polygons like this, and so forth. So using recast is a really good idea. Okay, so we'll just jump back to the demo map and we'll just explain exactly how a navigation mesh works in terms of pathing. So I'll just place down a navigation mesh. Actually, I'll describe one more thing that you'll probably want to know about when it comes to generating the navigation mesh, is that you can also specify volumes for the navigation mesh to actually build into. So pylons just have this cube that they build. So anything in that cube, anything that's determined to be something where you can walk on, will have a nav mesh on it. However, most levels don't tend to be cubes. They don't tend to work that way. They tend to be quite curvy. So this is where volumes comes into, this is where you use volumes to define an area of which to generate the navigation mesh. So say, for example, you had sort of a U-shaped level. And so you build it like this. You build volumes like this. You ensure that it encompasses the area that you actually want to pathfind in. Then you create a new volume. And you add a nav mesh bounds volume. And you do this for the actual shape that you want to build the navigation mesh. Right, so the next thing you need to do is you need to actually tell the pylon which navigation mesh bounds volumes to actually use. So I'll just move this out of the way. See that? So a really handy tip is you can use this button here to lock the selected actors. So this means that when you click on this, it won't switch to that. So if I click on that, I lock it. I can then click on that actor, it won't change, and then I can just assign them as I select them inside the editor. So I've got these three volumes. So you can see the pylon is no longer specifies the light blue box because the expansion volumes override the expansion radius, which defines the blue box. And you can also see it has yellow lines pointing to the volumes that it's actually using. So when I hit build paths, you can see that it's generating a nav mesh within those volumes. And if I use raycast, it generates it even faster. So it generates a simpler mesh as well. So if you have a particularly curvy level, or if you know that there's only a certain area that the AI absolutely needs pathing for, you can also really reduce the amount of memory that you use from pathing by just building pathing for these particular areas. Okay, so with that in mind, how exactly does a path node decide, or how exactly does an AI decide which polygons to use, and how does it generate a path based on the polygons? So the first thing it does is that it finds which polygon the pawn is in, for example, so the starting polygon, and then it finds which polygon is at the end. So it's a very similar theory in the same way that if you use path nodes, it finds the starting path node and it finds the end path node. And then it just traverses through the polygon tree, and the polygon tree is created by using polygon edges. So as it traverses through the polygons, it knows which polygons it has to hit in order to get to that last polygon. So it's a really similar idea, but because there are generally less polygons, it's quicker because the algorithm has less work to do. So now that we know the polygons, how does it actually generate the actual path? And I won't go too much into the detail of the mathematics there, but essentially it uses sort of a weighted best line of sight sort of type calculation. So because it knows, because the algorithm actually knows the true area, it can calculate based on the collision extent of the pawn, what sort of the quickest method to go to that end destination, or the quickest path to generate. And it's really flexible because this pawn or this box extent can be sort of any shape that it wants to be, any width and any size, and it will ensure to generate a path that's valid for that pawn. So there is quite a lot of information out there that talks about nav meshes and talks about why people should switch to them, why you should use them. Some advanced features that I won't go too much into detail this time is looking at things such as goal evaluators and filters and special things that you can do with the nav mesh. And if I give you an example, one really good example is inside an RTS game. If you have a harvester that wants to go to, say, mine some something on the ground, so say gems on the ground, you want it to pathfind not only in consideration of the obstacles in the map, because that one's an obvious one, but also in consideration of things such as enemy units. So you don't really want the pathfinder to just ignore the enemy units and have the harvester just run through the enemy's base or to run through a large group of enemies. You want the pathfinder to say, well, hey, I recognize that I should ignore these enemy units because they're covering this sort of area. And it's really nice because you can actually do those sorts of things using a nav mesh. Another thing that's also a really nice feature about the nav mesh is you can also dynamically create obstacles. And there is actually a UDM page which describes this. And I'll just go to that now. There we go. So with this ability has, this feature has been around for a long time, and you can create dynamic obstacles. So again, this works really well for games where you need to alter how pathing works. So let's say you have a game where you have, I don't know, a squad of Marines that follow you, and as you run around and do things in the level, maybe pillars collapse or something along those lines, and the pathing for the level has to change. And you can do that with this sort of thing. In the previous waves with using path nodes and waypoints, what you would have had to done in the past is turn off those waypoints so that they don't factor in to the pathing algorithm. However, once you've turned those path nodes off, you need to then really design a better system, or adding in more waypoints so that the AI still knows exactly how to pathfind through that obstacle or whatever else. And again, it's really rigid to change as well. So as soon as you change how the pillars fall on the map, or you have to start thinking, okay, well, these need to be predetermined. They can't just fall any way that they like, things like that. And it really restricts the design of the level. Whereas if you use something like navigation mesh, depending on which way the pillar decides to fall, it can just say, oh, this area now is blocked, and it creates a dynamic obstacle like this, and AI will just sort of know what to do. So that's really about it for the discussion of navigation meshes. So the key points to take home are basically that you may still use path nodes if you want to, and in some cases, it's probably going to be easier to use path nodes. So path nodes are still useful if you want the AI to be able to pathfind, but in a really predictable manner. So say, for example, you have a tower defense game, and you have some AI which can walk along a path that's been generated by, I don't know, the level designer, and the level designer has said, here is the path that the AI absolutely needs to walk in. And you want to use you still want to use pathfinding because you do want to allow them to walk off the path, just in case they want to attack a tower or something like that. But if the tower has died while they're attacking it, you want them to go back onto that path so they can continue down to the castle. So, because the waypoints only provide one way for the enemies to walk in, it provides a really predictable way of them navigating through the map. And you want this behavior in a tower defense game because you want them to be able to, you want the player to place towers in a way that he knows that the towers are going to be effective. So that's one area where you may still want to use path nodes. Where you want to use navigation meshes is where you want to have levels that are quite unpredictable as such. You know, they change a lot. Maybe for a tower defense game, let's say you have an area that the enemy can walk through, and your job as the tower builder or as the player is to build a giant maze. Now, you could potentially waypoint in a way that is, it either tries to forward predict or it aligns all these path nodes to a grid or something, and you turn each path node off as the player builds on them, just things like that. It's a really cumbersome way of doing it. Whereas if you say, okay, this entire area is just a nav mesh, and as players build towers, we just subtract away from that nav mesh too, so that the AI doesn't try to walk through towers. And as you can see, that is probably the best method to go in. All right, and that's about does it for the for this introduction to waypoints and navigation meshes. So we're going to move on, and we're going to start talking more about, okay, so how does the AI actually, how do we set up an AI? How do we get the game to actually spawn in some AI and stuff? So we'll move on to discussing that in the next chapter. So in this chapter, we're going to have a look at some of the improvements I have made to the task system. So one of the first things that I added was a new Kismet node, which allows you to check whether a pawn is on a particular team. And this is important because you don't really want, say for example, a task for the red team being able to be achieved by somebody on the blue team. So if, for example, let's say a red team member needs to reach a certain area of the map, you don't really want a blue team member running there and then triggering that and completing the task for the red team. So let's just have a breakdown of this Kismet node. So the first thing is that it's a sequence condition, and essentially what this means is that this Kismet node is used as sort of a if or else sort of a in that sort of manner. So we've got two variables here, object instigator and int team index, and basically these ones just store the instigator, so that points to which pawn we're checking the condition against, and we've got team index is the team index variable that the level designer puts in. So as with all Kismet nodes, when they get activated, this event gets called event activated. So as we go down, first thing we do is we publish the linked variable values. So that is to say that the Kismet variables that are linked to this Kismet node, their values are copied from the Kismet over to script. So now how this works is that it iterates through all the variable links. So it iterates through the variable links here. It then matches the property name with the variable name. So this is done inside native code. And it then, if it finds a match, it then copies the value of the Kismet variable, such as object or int, and it copies them into instigator or team index, which is matched through here. So that's a nice, easy way of scanning through all of the variable links to either check that they're correct, check if they're valid, or anything like that. The next thing we do, because we want to compare whether this pawn belongs to a certain team, we need to grab the player replication info. So we're not entirely sure what value is going to be inside instigator because it only is stored as an object. So we need to typecast it first into either a controller or a pawn. It usually is either one of those two things. So we attempt to typecast it as a controller in this line here. So we do the typecast, we assign the typecast value into the controller variable, which is declared here. If it succeeds, the controller value will not be none. If it fails, so let's say instigator actually pointed to a pawn, that won't cast into a controller, so it'll fail and it'll go down here. But if it succeeds, we can pull the player replication info from the reference inside the controller. Otherwise, if the controller typecast fails, it will go down into this block here. We then attempt to cast it as a pawn. And again, we do the same thing. We check if the pawn typecast succeeded. And if it succeeds, we pull the player replication info out from the pawn. Okay, so after we've done that, we double check to make sure the player replication info has been successfully grabbed from either the pawn or the controller. We then check whether the player replication info actually has a team reference, and if it doesn't, then the rest of this isn't going to work. So if that's the case, we return, we do an early exit out if it doesn't succeed. We then trigger true or false, depending on whether the team indexes match. So you will have noticed here that I've got two output links, and that's 0 to 1, so these match these ones here. So if the team index equals to the team index that Level Designer provided, then we want to trigger that to true. So the output link that's marked as true will be triggered. But if it's not, we trigger the other one to true, and that basically is triggering the false output there. Okay, so let's have a look at this inside Unreal Ed to see what that actually looks like. So when we want to create a new one, we go new condition, and it's here, is on team. So as you can see here, we've got the instigator variable link, we've got the team index variable link, and that's done by setting this up. We've got two output links, true and a false, and again that's also set up inside the default properties here. And we have an input link called in, which is here. So if I want to compare a touch event, we've got one here, so we'll just delete that. So, okay, so how's this used? So when this trigger gets touched, it outputs an instigator. So this instigator usually is the pawn that touched the trigger. So it outputs into this Kismet variable object here. And then it then triggers the isOnTeam Kismet node. So that calls the activated event. We then pull these values into the variable. So these Kismet variables here, their values are copied into the UnrealScript values up here. And then this block of code is then run. So if the pawn, which is here, matches team index or is on team 0, then this will return true, and then we proceed with the rest of the logic here. If it's false, it will come out to here, and we can do something else such as play a sound or play some other particle effects, but in this case, nothing gets done, so nothing happens. So that's one real simple way that we can add a new Kismet node to further enhance how level designers can design tasks for their levels. So for example, you can create a new Kismet node which checks if the instigator has a particular inventory item. So for example, maybe an assault task could be that the player has to pick this thing up, and then as a team they have to carry it all the way down somewhere else. You can make tasks which check for different types of weapon damage, or different types of classes can only do this thing. So there are a lot of options there. And if you're the programmer, you can create these and make it easier for the level designer, so that you don't have to program this inside UnrealScript. Okay, so the next thing we're going to do is look at the advanced Kismet setup that I've got in the new map. And basically one of the essential problems of the initial iteration that we saw in the DVD number 2 was that the triggers and so forth, they're all just set up reasonably simply just to test the whole thing. And that works initially until you start to realize that you can do the tasks out of order, you can be on the red team or the blue team to do the tasks and so on. So now a lot of the features that we're going to use are already inside Kismet. So it's just a matter of revealing those options so that they can be used. So the first thing is that to prevent the tasks being done out of order, the first thing we do is when the map gets started, when the level gets loaded, we have a, oh, this is linked to the wrong one. We have a toggle here which can turn off a whole bunch of triggers or turn off a whole bunch of Kismet events. So we link up the level loader to a toggle which turns off a whole bunch of events. So as you can see here, I've left the first task alone. So that doesn't get initially disabled, but these ones do. So the second task, the touch event gets disabled, and the third task, the touch event also gets disabled. Okay, so how do we proceed from here? So if we break down each thing, in task number 1, we can see that we create the initial task, and we do this in the same fashion as we did in DVD number 2, and then we have a touch trigger, or a touch Kismet event. We then check if it's on the same team, because we want to make sure that the actual team that's been assigned the task is the one that touches the trigger. We then have another condition to ensure that only servers evaluate this and not the clients. We then complete the task. We then enable the next task by turning it on. So as you can see here, that event gets put down here. So this gets enabled. And as we go further down, we then complete another task. And I'll explain this one a little bit later. We complete another task, and then we disable the task that was just completed. So this prevents the task from retriggering again and again and again. And the reason why we have that is because since now we're checking all the time who is touching this trigger, we need to actually set the max trigger count to 0. And that's because, let's say for example, a blue team pawn touches this trigger. It's going to trigger all of this, but it's going to fail here because the pawn is on the blue team, which is usually a team index of 1. Now, if this had a max trigger count of 1, a red team member later on couldn't trigger this again because it's already hit the max trigger count. So that's why we need to disable it. And then, of course, from here, as we go through here, this is done on this task completed event node gets triggered on both the server and the client. And what happens here is that we disable a whole bunch of player starts and enable the next set of player starts. And this is to allow sections of the level to be closed off, or to be turned off, I suppose, because players no longer spawn in there. Okay. So, and this just sort of repeats itself. So again, this one gets enabled when task 1 is complete, and this goes through. It enables the next task. As you can see, it goes down, enables the next task, and it disables itself. And that's for the same reason. Okay, so the next thing we want to look at is in DVD number 2, even though I showed you how to create the tasks, I didn't really sort of iterate much over how to create a task list for the red team and the blue team. And normally with these assault games, you have the red team doing a series of actions, and you have the blue team defending, or you have the blue team preventing the red team from doing those actions. So we need to synchronize somehow what happens when the red team does this, then the blue team's objectives need to change. So essentially, in this task here, all we want is the players is to reach the waypoint. So, for the blue team, basically what we want to do is just tell the blue team to defend a waypoint. So this is sort of the opposite. Essentially what we're doing here, we're creating a task, we give it a name such as, defend the landing zone, and basically the red or the blue team can never actually finish this goal, or finish this task, I should say. Essentially what happens is that the red team has been assigned to finish this task, and the blue team just continues this task until the red team has finished their end. So in this case, when the red team finally reaches the waypoint, it then completes the blue task as well, because in that sense, the blue team has failed this task, and now they move on to the next one. So that's kind of an easy way to structure it, and it ensures that you have both a red team and a blue team actively fighting each other, because the tasks are related, even though they are considered to be separate objects here. Other than that, that's really about the advanced level, or that's sort of the improvements that I've done to the Kismet task system. Some pretty minor ones, but reasonably important, and hopefully it gives you more you get a chance to realize that you can actually do more with this task system. There are some other new nodes here as well, such as evaluate task, and these are really just for the AI. But when you jump to the AI chapter, you'll see how these are being used. All right. So now we're going to be talking about the general structure of AI inside an Unreal Engine 3 game. So as you will have known from DVD number 1, I talked a lot about controllers, pawns, player replication info, and that sort of general setup. And when we talk about AI, it really comes back to those topics again. So initially, when we talked about controllers, we talked about controllers take possession of a pawn and then they forward input to that pawn, and the pawn sort of reacts to those inputs. So in this case, if you ask a player controller to possess a pawn and you press the W key, then the pawn knows that it should walk forward, or it's given an acceleration to walk forwards. And in a lot of ways, this is sort of essentially what AI is doing as well. All it's doing is it takes possession of a pawn, and then it gives the pawn some values such as acceleration, that asks it to fire its weapon and so forth, to give the impression to players that they're playing against somebody else in the match as well. So I'm going to briefly talk about how we actually add bots. So bots are mostly server-side. So, well, they're all server-side. The results of what bots do or what bots think is replicated through pawns. So the really nice thing about doing AI is that most of the time you don't generally need to worry too much about replication and that sort of thing, because AI don't need to really talk to clients, and clients don't interact or really do anything to the AI other than doing things that the server already knows about, such as shooting weapons at AI and so forth. So when you code AI, generally you don't need to think too much about it in terms of networking and replication. So one of the first things I did was I re-added the add bots console command so that I can very easily add some bots. And how do these work? So if we find the function add bots, there we go. So all I'm doing is iterating from 0 to bot count, and I spawn that many AI controllers. And that's basically all I do. I also assign them to a default team. So, and with the default team, that's 255, and basically that just means that the game will just assign them to the smallest team. So if the player adds 3 bots, then he's going to have 1 other bot on his team and 2 other bots on another team. So, okay. So this is very simple. So now that we have some AI controllers floating around, how does the game actually give them pawns and so forth to spawn with? So when the match is in progress, this match timer gets called every 1 second, as it's been set up here, and it starts bots. And this is the same way in that it starts humans. So this function is actually defined in game info. So if we take a peek at game info, start bots, you can see that basically it iterates through the controllers in the world, and it just tests, if it's not a player controller, but it is a player. So one of the distinctions that you can make between AI, and this sort of is a legacy sort of a thing from Unreal Tournament days, is that AI can be monsters as such as in the original Unreal you had sort of the gnarly cow, which had a controller as well. Well, it didn't really have a controller back then, but if we think Unreal Tournament 2004, we think about the invasion mode. You had some enemies that would spawn in. They wouldn't be considered as players because they were sort of the creeps that could run around and still use the controller class and so forth. And then you had bots that pretended to be players. So p.b as player is really just a legacy thing. Anyway, so what it does, it starts the bots, and it starts them by going to the dead state. Or in this case, in standalone mode, we restart the player. The bots themselves will restart themselves. Okay, so when we jump into restart player and have a look at that function, it's basically the same thing. If we check in game info, because we actually overrided restart player, all we're doing there is basically just checking to make sure that the player has actually assigned themselves a class archetype, and then we can restart the player. So we've got to make sure that the AIs do that as well. So how does the game know which AI to actually spawn? In this case, when I've added the bots, I've just given it a class name. So it spawns Assault AI Controller. So let's have a peek and have an examination of Assault AI Controller. So it extends off AI Controller, which is a base class that's also found inside Engine. And that in itself extends from Controller. It basically has a bunch of native functions and also some debugging and so forth and so on. So it's just a useful class to extend just in case we want to use some of the functionality inside there. So we have some properties here. So I won't go into these two just yet, but I will go into this one here. So Assault AI properties, essentially, as you start making your AI and you start layering on some of the game mechanics, you want to be able to control certain things, such as how far the AI can see, possibly the AI's response time, all of those aspects. And rather than storing those properties inside the class, you can store them inside a object archetype. So it makes it really easy for the game designer to either make the AI much more difficult or make the AI much more easier, those sorts of things. And also you could probably exchange these AI properties out for things such as if the game is in easy mode, maybe they can't see as far, they are not as accurate, they have a longer response time, etc., etc. So if we look at that class now, you can see it's just an object class, and it has a sight radius and sight angle. And we'll get back to these values soon, but just know that I'm storing some values inside the archetype. Okay, so post begin play. So the first thing we do is call the super post begin play, because if you remember from controller, if the controller is determined to be a player, which means that B as player is equal to true, we can see that in the default properties down here, B as player is equal to true, it spawns a player replication info for that controller. And we can actually have a look at that class now. Yeah, here we are. So it calls this function here, init player replication info, inside post begin play, if only if B as player is true. So if you remember from the previous thing, before a bot can restart itself, it has to have a valid character class or a valid class. And so what we do is we grab the assault player replication info from the spawned player replication info that was done in the super of the post begin play. We typecast it. If the typecast succeeds, we then set the current class, and essentially we set it to a random class. So I haven't really added any logic for the teams to decide, if somebody on the team already has a link gun, then I really should be a rocket launcher. Things like that. I'll leave that to the exercise to you. Not particularly too hard to do. You can just scan through all the controllers that are inside the current team, and if there is a mismatch between the different types of character classes, then you just set it to a different one. So, okay, so next thing we're going to look at is what happens when the controller possesses a pawn. So when the controller possesses a pawn, the thing that we really want to do is start a timer, which says what to do. Now, with anything with programming, this is one way of doing things. And I'm not going to go out there and say this is the absolute best and only way of doing things. So there are lots of different ways to write AI, and this is the way I like to write it because it's a really simple way of representing AI. But as you layer more and more sort of logic to the AI becomes more and more difficult, or it becomes more and more interesting. It does different things and so forth. So I really like to design code in a simple way that's straightforward. So anyway, I have a timer which loops every 0.05 of a second, and it calls a function called what to do. And essentially this what to do function is basically the grand logic of what the AI should be doing at any given point in time. And one of the nice things is that with a simple setup like this, you're not running this every single tick, so it isn't going to be consuming tons and tons of processing power from your CPU. You can randomize this value, so you can have a rand range between 0.04 and 0.067, and that way at least AI isn't going to hit the CPU all at the same time, so you can shuffle those values a little bit so that it spreads out the calculations evenly between the AIs. Now, so there are some little tricks that you can do there. You could also increase these values depending on the difficulty so that the AI takes longer to respond to its environment and that sort of thing. So you might be asking, so when and where is possess being called? Well, when a controller is given a pawn inside restart player, it asks the controller to possess that pawn. And when the controller possesses that pawn, it calls this function. So that's an easy link up. Okay, so now we're going to be diving into what we consider the main loop of the AI. So the AI is looping this function, which is called what to do, and we figure out what it's doing. You will have also noticed a tick function, and I'll get back to that soon. Okay, so this is the sort of the master function, as you like, that determines exactly what the AI is going to do at any given point in time. So the first thing it does, when it gets into this function due to the timer, it checks if the pawn is valid, and it checks if it has an AI properties. So essentially, we're going to start using some of those values inside this. So one of the things that I generally like to do is to give tasks a certain priority. So for example, if you have a RTS game and you have some harvester AI, maybe the absolute priority that it needs to have is to avoid enemies, because you don't want, players don't want their harvesters being attacked and dying when they're not sort of in control of them. So you may put at the high, on the priority list, at the very top, you may say that if they're scanned for enemies and if there are any enemies near me, then run away. If it's for a unit that can attack, maybe it's the opposite way around. If you have enemies nearby, I should attack them, that sort of thing. So in this case, I've decided to make the pickups a higher priority than anything else. So the AI then goes down, it typecasts the pawn into an assault pawn. And the first thing I do is I check if the bot needs any ammo. So the first thing that happens is that both the weapon itself gets typecast into an assault weapon, and the weapon's object archetype also gets typecast into weapon. So what we have is an instance of the weapon, that is assault weapon, and a assault weapon cast of the object archetype of the weapon. So this will all be explained very soon. So we double check that those typecasted values succeeded, and then we call assault weapon needs ammo pickup. So essentially, the controller is asking the pawn's weapon, do I need more ammo? So let's check that function and see what that does. So the needs ammo pickup. So basically, it returns a true or false. So basically, it analyzes, is the ammo count below max ammo counter times 0.5? So is the current ammo amount less than half of the maximum amount of ammo? So let's say the maximum amount of ammo is 100, half of that is 50. If the ammo count is below 50, then I need ammo. But we also have this AND condition here, and that's basically checking if a timer is active. So if the ammo regeneration timer is active, then we basically the ammo regeneration timer is stopping the weapon from regenerating ammo. And so if that timer is active, then yes, the weapon also needs a pickup as well. So basically we're checking ammo has to be less than half of the maximum amount, and the ammo regeneration timer has to be turned on. So the gun has low ammo and is not regenerating ammo at this current time. So if that's true, we then find the nearest ammo pickup. So in this case, one of the things that I generally like to do with AI is that I assume that AI knows the whole level layout. The AI doesn't need to explore the levels to figure out where things are. The AI just knows where everything is. And I guess you can get away with that assumption because eventually good players are going to know the whole level. They're going to know the whole layout of where everything is. So you can assume AI just already know that. So with that assumption, one of the things we can do to find the nearest ammo pickup available, we can simply iterate through the entire list of dynamic actors, and we pick out all the actors that are assault pickup factory ammo. We ensure that the assault pickup ammo factory, the assault pickup factory ammo is available to be picked up, so it's in the pickup state. And we also ensure that the assault pickup factory ammo has a valid, it has the controller's weapons object archetype as a valid weapon archetype. Because there's no use for an AI to run to a pickup factory for the wrong ammo, because nothing's going to happen. So that's going to be one of its checks. So basically any of the assault pickup factory ammos that's being checked in this highlighted block here is ready to be picked up and is also the correct factory in order to replenish ammo. So from there, we calculate a rating. So we want to find the one with a short, and the one that's not too far away from the player. So the one that's nearest to the controller, sorry. And basically, if we do an inverse of the distance, that'll get progressively smaller. So as the things are further and further away, the rating value gets smaller and smaller. So for example, if a pickup was 1024 away, we do, right, it has a rating value of 0.0009. If it's only 512 away, it has a slightly larger value. Yeah. So basically, we're looking for the higher rating. So we then we go down and we go to best ammo factory is equal to none, or the rating is higher than the best rating. We then assign the best ammo rating and the best rating here. So basically, we're just filtering down through all of the available pickups that are valid, and we're just picking out the best one. And in this case, the best one is the one considered to be the closest to the controller's pawn. If we've found the best ammo factory, we then set the destination position, and we go into the moving state if the controller is not already in it. We then break out from this function because we're done. The AI has already decided that it needs more ammo. So it says, okay, well, I'm done. Okay. So we touched on a few things. We touched on set destination position and go to state moving. Now, I'm going to discuss these a bit afterwards. I'm going to continue down through the logic tree so that you can see what else the AI is doing. And then we can examine each different bit of what the AI ends up doing. So right now it's still deciding what to do. So let's say that the AI doesn't need ammo. So it goes down and it says, okay, do I need health? So now it does assault pawn needs health. Now, if you've already watched the chapter where I discuss how cyborgs, when they pick up health, they regenerate shields, but they don't gain any new health. And if humans pick up a health pack, then they do gain some health. So there are some differences there. So needs health pickup. So let's check how that function works. So basically all it does here is for humans, if the health is below health max times half. So if my health is currently below half of the maximum health, so if the maximum health is 100, if it's below 50, then I need a health pickup. And for cyborgs, I've overridden that function. So it returns true if the shield is below half of the maximum shield amount, and if the shield regeneration timer is not currently active. So shields are not being regenerated. So this is the AI controller doesn't really need to know whether it's controlling a cyborg or whether it's controlling a human, because the behavior of deciding whether it needs a health pickup is determined by the pawn itself. And since we can use object-oriented code in this case, it makes a nice clean interface for the AI controller to know exactly what it actually needs to do, depending on whether it's a cyborg or human. If I didn't code this in an object-oriented way, I'd probably write, cyborg.pawn doesn't need health and evaluate it here, and then I'd say else if this is a human, then evaluate it here. But that's not a very nice way of doing things. So we do a very similar setup to where it finds out the closest ammo. So we're doing a dynamic axis again. We ensure that the assault pickup factory underscore health is available for pickup, so it has to be in that state. And we look for the best one. And again, we do the same thing here. So if there is a health factory to go to, we set the destination position, and if it's not in the moving state, we go to the moving state, and then we break out, we return. So because we're done, we're sorted, we know what to do now. Okay. So there are only two types of pickups in this version of the game. So that's all that there really needs to be. In later revisions, if maybe players can drop weapons when they die, maybe players will drop gold, or things like that. The AI also doesn't specifically hunt for things like the berserk or the damage, the double damage pickups. I'll leave that as an exercise up to you as to how you might write one. So maybe the AI doesn't really need to evaluate whether or not it needs to grab the double damage or the berserk. It just always tries to. But as a game mechanic thing, what you could add is, can they actually see it? And if they can see it, and if they can see that it's ready for pickup, then they should try to pick it up. Because otherwise you have AI that just dashes for the berserk and the double damage all the time, and that doesn't feel very fun. But I'll leave that as an exercise to you. Okay, so if we've determined that the AI controller doesn't need any pickups, it then moves down. So the next important thing is handling enemies. What do I do if enemies are near me, and what do I do with my current enemy, and so forth. So the first thing we have is if current enemy does not equal to none. So we're evaluating the current enemy, and current enemy is just a reference to an actor. So how we go on from here is that we first cast it as an assault pawn. And the reason why we do that is because I want current enemy to be an actor reference so that I can put any kind of reference I want in there. So if one of the tasks for the AI is to destroy some storage tanks or something like that, then I can put a reference to those storage tanks inside the current enemy. So if it was just a pawn, then I couldn't do that anymore. But of course, one of the downsides is that I need to double check, whether the current enemy, which is a pawn, is still valid. So the first thing I need to do is typecast that. I check it's valid, and then I check, if the pawn has no more health, or if I don't have line of sight anymore, then my current enemy, I set it back to none. And this basically allows the AI to not cheat, I suppose. So if I didn't have this line here, let's say a AI was chasing after you and you ran behind a wall, the AI could theoretically still know where you are because the AI just gets given a bunch of values, for example. So by doing a trace, we figure out, oh, there's a wall there, the AI can't see you, so it just forgets about you. Of course, you can extend that logic and you can say, okay, so the player was last seen at this location. So get the AI to run there and have a look around. It depends. If you're making a game where stealth is a big thing in your game, then you may want to give AI the option to start scouting around in the area where they last saw you. And maybe they'll hunt around, and if they see you again, they'll start chasing you and attacking you, and so on and so on. But, you know, I also check if the current enemy has died or not. So I check the health status. And obviously, if the enemy has died, there's no point to continue pursuing that enemy. So we set the current enemy to none on that condition as well. Okay, so what do we do if the current enemy is actually none? So the obvious thing to do is we want to scan and we want to check if there's anyone within the bot's vision to attack. So one of the big questions that seems to get thrown around a lot in the UDK forums is a lot of people asking, how do we make bots see? How do they detect things? How what can we do? And some people might start using things like touch events and bump events and so on and so on. But there's really an easy way of doing it, and that's really just using the actor searching type functions. And one of the useful ones is called visible colliding actors. And essentially what that does is that for any given actor who casts a visible colliding actors, they basically shoot out a collision cylinder. And for all the actors within that collision cylinder, it checks, are they of a particular type or a particular class in this case? And do we have line of sight to them, thus the visible keyword, and so on and so on. So this iterator here is actually defined inside actor. So if you want to find out more information about it, look up this, or we can actually look that up. So as you can see, it returns all visibles, not hidden actors within a radius, for which a trace from lock, or the caller's location, to that actor's location does not hit the world. So this enables pawns to not be able to see through walls and so forth. Okay. So for all the pawns we pick up, now one of the things that I wanted to do with AI, to give it a little bit slightly more realistic feel, is that AI can't see behind themselves. If we were to use this function, it doesn't do a check whether or not the AI can actually see them, whether they can see them behind the back of their heads or whatever else. So we've got to calculate that ourselves. But before we do those expensive calculations, we need to run a few checks. So the first thing we do is we need to actually check whether this is an actual enemy or not, because this is going to return all sorts of pawns. So first of all, we double check the assault pawn that we found if it's a player replication info, if it has a player replication info, sorry. We then check our own player replication if it does not equal none, and then we just check the teams. If the teams are equal, then that pawn is on the same team as me, so I don't need to consider that pawn as a potential enemy. So let's say we found a pawn and it's not on the same team as me, so it's actually a potential enemy. So I need to double check whether or not the pawn is within my sight cone or not. And a really easy way to check that is to use a dot product between two vectors. So we do a dot product between the pawn direction, and the pawn direction is found by doing converting the pawn's rotation to a vector. So that gives you a direction vector of the pawn's rotation. So it essentially gives you a direction vector of where the pawn is looking. And then the actor to pawn direction gives you the direction of the pawn to where it should be facing in order to see the potential enemy in question. So by doing a dot product, we can figure out how close those values are as a singular float. So if the values are very, very close together, then we get a result between that's close to 1. If the results are perpendicular to each other, then we get a result of about 0. And if the result is, if the vector directions are way out, so say for example the pawn is facing forward and the direction in order to face the potential enemy is behind me, that's going to give you a negative value. So by doing a dot product, we can determine if that dot product is above or equal to AI property's sight angle. So what is the sight angle? So the sight angle is the angle of sight that the AI can see in. So this prevents the AI from being able to see behind himself. So most of the time, sight angle is probably going to float around the 0.85 value because you want to give some leeway to have a cone so that AI can see further out. And this is a very traditional way of sort of doing a sight cone and so forth. So if that potential enemy is within range of my vision and within my angle of view, then I add that pawn to the potential enemies list. And we don't want to immediately assign an enemy just yet. We want to build a potential enemies list so that the AI can rate them and see whether or not it's worth attacking them or not. Or, so for example, if the player sees 3 or 4 enemies in front of them, we don't want to just pick the first one that we find. We want to compile a list, which is what we're doing here, and then go through the list and find out which is the one that we should attack. So from here, we evaluate the list of potential enemies. So essentially, we iterate through the potential enemies. We calculate a rating for the enemy. Right now, this is a really simplistic way of calculating the enemy rating, and that's literally the closer the enemy is, the bigger or the more likely the AI should target them as an enemy. So you can also add some other parameters as well. So for example, if the AI is carrying a big weapon or something like that, like say the rocket launcher, then the AI can say, okay, I should attack him. Or you can even do weapon comparisons. So if the AI is carrying a link gun, and if the AI is about to select a guy with a rocket launcher as his enemy, maybe he should say, well, I have a link gun. I really shouldn't attack this guy because that's going to be dangerous. Another thing you might want to do is now we know that in DVD2 we added some special effects. So when the AI gets hit by a shock rifle, when the cyborg gets hit by a shock rifle, the screen goes bright white, and when the humans get hit by a rocket launcher, their screen goes all blurry. So you may want to add something that says, okay, if I am a cyborg, I want to avoid potential enemies that carry the shock rifle because they do some damaging effects to me. They can stun me for a bit. And you can add a random value depending on how bold the AI is. That a random value can sort of suggest that an AI can be a bit more bold as such. But this is a really simple way to evaluate whether or not a potential enemy should be chosen. So for now, I've kept it really simple, and I basically said that an AI will choose the player that's closest to him, or choose another controller that's just another pawn that's closest to him as his enemy. So if there was a current enemy, if their enemy was found, I set the focal point to the current enemy location. So the AI is going to start focusing towards that current enemy, and I set the destination position to the enemy's location. If the controller is not in the attacking state, it then goes into the attacking state, and then I return out because I'm done. The bot knows what to do now, so it knows that it needs to attack a player or attack another pawn. Okay, so if it doesn't find all of that, it doesn't need pickups, and it doesn't need to attack anybody, the AI then says, okay, well, this is the assault game, so I need to actually accomplish the tasks. I need to do something. I need to do whatever it needs to actually be able to win the game. So the way I've decided to do this is because early on in DVD2, the initial design of the task system was that it was built in Kismet. Now, it could have been possible to design an AI that could have encompassed every possible solution of how to achieve a task. But of course, this breaks the the actual this breaks the concept of allowing level designers to be free in how they want to actually craft their levels and design the tasks. Because now you're saying that even though you can do all this stuff in Kismet, design the tasks in Kismet, the AI won't work unless you do it this particular way. So you're introducing constraint if we were to do it that way. So the way I ended up resolving this was actually to use Kismet to evaluate how an AI should behave. Now, this is actually pretty complex, so I'm actually going to separate this out into a different chapter. And I'm going to sort of go and sort of talk about the rest of the AI controller in this chapter. But rest assured, in another chapter, we'll talk more about this exact thing here. Okay. And if for some reason the AI doesn't want to handle any pickups, doesn't want to handle any nearby enemies, and doesn't want to do a task, we at least need to drop them to the ground so that something happens. So this is why I've set this pawn physics, set movement physics. So it just means they don't float up in the middle of the air. Okay, so there are certain functions that sound like they're obvious as to what they do, but we need to figure out how they work. So these functions that I'm talking about was ones called set focal point and set destination position. So what does set focal point do? So as it turns out, it's a function that exists inside controller. There we go. So it sets the focal point as an absolute position or offset from a base. And we also have one that's just get focal point, and that returns the final position that the controller should be looking at. So these two functions here determine where AI should be looking at. And what I have in the tick function is basically that to rotate the pawn so that it's always eventually looking at the focal point. So this is a really nice sort of a setup. So if you want the pawn, if the AI needs the pawn to focus on anything, it could be focusing on the AI to attack them. It could be focusing where they should be running to so it doesn't look like they're strafing everywhere. If they need to look at you for any reason, things like that. You can just set the focal point to somewhere within the world, and the pawn will just turn there. And that's a nice, easy way of setting it up. So what does set destination position do? Again, here it's a native function that's inside controller. So set destination position, set destination as absolute position or offset from base, and we also have a get destination position. So we are essentially using this to allow us to indicate to the controller, or the controller says, I want to be here. And one of the nice things that we can use is a Boolean called be precise destination. Now, when be precise destination is true, it forces all velocity to be directed towards reaching destination, which is set by set destination position. So you will have noticed that because I'm using this, and because I'm using this to control the velocity, I get some really fine control here. I can just enable or disable pre-precise destination when I've decided that an AI has reached somewhere. And of course, one of the things that I don't use anymore is some older latent functions called move to and move towards. So these were some functions that you could have used back in the past, and you can still use them today to tell an AI to move to a certain location in the map. I prefer not to use these at the moment. I personally found set destination position, set focal point, be precise destination to be a lot more controllable and manageable, and I prefer using them. So you won't see me using these latent functions here. Okay, so now we know how and what I'm doing in order to make the AI move its pawn. So I'm setting a focal point to make the pawn rotate to look at that point, and I'm setting a destination position, and then setting the be precise destination flag to true, it makes the pawn run to that destination position. Okay, so the next thing we're going to look at is the state called moving. So when the AI controller goes into a state moving, as we have here in the comments, in this state the AI is moving to a location. So in this state, I have here a state, basically a state loop. And the reason why I have a state loop is just in case I want to use a latent function. Now, a latent function is basically a function which is a function which exists through several ticks. So, and sometimes if I want to use them, I can't put this inside tick, for example. I have to use a state loop. So anyway, when the state first enters, it runs this thing here called begin. It goes down. First thing we check for is if the pawn is still valid. If the pawn is dead or anything like that, we want to get out of this moving state and go into the dead state. Second thing we do is we double check that the pawn is able to move around on the ground. So for the pawn to be able to move around in the ground, the pawn physics has to be at least phys walking, or it has to be one of those. There's another one called phys nav mesh walking, I think. But if it's not in the phys walking state, we basically call this set movement physics. And what that does is that it ensures that the pawn is either in the falling physics state or it's in the walking physics state. But we can look it up here. So here we are. If the physics doesn't equal phys falling, then phys falling. When the pawn lands on the ground, it automatically switches. So when the landed event gets called, it does this. So, and in native code, it automatically switches it to the walking physics. So I set be precise destination to false because we don't want the AI to try to have we don't want the AI to try to run while he's falling. So I turn that to false. I then use a latent function called sleep. And basically sleep just tells it to stop doing something for X amount of time. I put in here 0.f. And basically what I found is that when you use this, it tells it to sleep for at least this tick and then carry on the next tick. So I sleep for 0 seconds or so, and then I go back to begin. And basically this is a little loop that keeps going round and round and round, and it only stops this loop when the pawn is able to walk. Okay, so the next thing we do is we check if the pawn can directly reach a destination. So the way we check is to use a line of sight. So we can see that by looking at this function here. So again, I check if the pawn is valid. I grab the pathing extent. So basically, I generate a box that's 1 unit tall and 1 unit long, and I use the pawn get collision radius. So basically, I'm generating a box extent which is the same width as the pawn, and then I do a fast trace. Now, if that box extent or if that non-zero extent trace hits anything, then it's determined that if the pawn was to walk in a straight line to go to the destination position, he won't be able to get there because he'll collide into something. So, but if the non-zero extent trace doesn't hit anything, doesn't hit world geometry or anything, then it is determined that the AI can just move there without having to use anything like pathfinding. So often you want to do this really early on, because if you can avoid doing pathfinding when it's not necessary, then you basically speed up and you remove some of the CPU costs for running the AI. So if it can directly reach the destination, the first thing we do is we set the focal point to the destination position so that the pawn looks where so the AI looks where it wants to head into. We set be precise destination to true, and we skip past this block here and we go straight to the has reached destination block. Okay, so basically has reached destination block just essentially checks, have I reached my final destination? So let's say that the AI can't move directly to the destination that it wants to be in. So if that's the case, this block that I've highlighted here won't be executed. It'll skip past that and go down to here to move via pathing. So now we know that we need to generate a path. So we use a function here called generate path to, and we grab saying that we want to generate a path to destination position, and we want to use this value here of the collision radius and have a value true. So let's actually have a look at this function to see what we're doing. So, okay, so this is the goal. This is the within distance. So basically what we're saying to the Pathfinder is that, you don't need to be bang on at the goal. You can just sort of be around that goal. This is sort of the radius. So in this case, we're using a pawn collision radius. So, pawns will get close enough to it, basically. And we allow a partial path. So one of the nice things about pathing in Unreal is that sometimes pathing can be expensive because, it's a recursive function. So basically, if you're telling the AI to go from one end of the map to all the way to the other end of the map, that's going to be a long calculation time. So you can say, calculate a couple of steps ahead, and then as the AI is moving a couple of steps ahead, it just returns that. So, okay, so basically the rest of this is handled by native code. We basically just set up the pathfinding. So we use these static functions here. Now, this has been used from the UDN. So the UDN has some good examples of how to use these. So anyway, we just go, we want to move toward a point, to the goal. We want to, the Pathfinder's goal should be at this location. We then set the final destination of the navigation handle so that the navigation handle knows where it ultimately wants to go. And then we return whether or not we could generate a path or not. So sometimes you might provide an impossible goal for the Pathfinder to find. So, for example, let's say you want it to go somewhere where there is no nav mesh. Well, it can't find a path if there's no nav mesh there, so it'll return false. So that gives you an opportunity to do something there. Okay, so we generate a path. If that succeeds, we then go to navigation handle and we grab the next move location. So this is the reason why we have this variable here, because we need to use that as a temporary sort of a value. So next move location. So, basically after we've generated a path for the AI to follow, we just need to pop the where it should go to next off the route list. So and the route list is stored inside the navigation handle. So we set the destination position to the next move location. We then set the focal point to the destination position, so the arrow will look towards where it wants to move in. We set be precise destination to true. Now we know that we're not going to reach the destination from here, so we go straight back to the beginning, and again we double check. We go back to the beginning and it passes down, and basically it just checks, can we move there directly? If it can't, continue to pathfind. So basically the arrow will just iteratively keep trying to eventually get to its goal. Now, if the pathfinding fails, it goes straight to end. And basically, end just exits out of this state. So this can happen sometimes if an AI falls off and goes into somewhere that it can't actually, where there's no nav mesh and it can't continue to path. So we don't want to keep running this loop when really it should just get out because it can't pathfind. So eventually we get down to has reached destination, either by this or by this. So the first thing we do is we check, have you reached the destination? So let's have a look at this function to see. Has reached destination. So all it's asking is that, is the v squared 2D, is the distance between the pawn location and the destination position, are they within the check distance? And these values are, by default, the collision radius of the pawn and the destination position. So basically it's saying, are we close enough to the destination? And if we're not, we go back to the beginning. If we are, we then check, is the pawn close enough, or has he reached the final destination position? And the final destination is what we've set up here. And the reason why we do this is because if the AI was using pathfinding, the set destination position gets changed. That value gets changed, but the final destination doesn't change very much. So yeah, so we continue to use that. So we set the focal point, we then set the destination position, and we move to the destination position. So one thing I've noticed is that this should actually be the final destination. So it shouldn't actually be the get destination position. So we can make that change now. Like so. Okay, so that's basically the moving state. And now we want to check out the attacking state. So in this state, the AI is attacking an actor. So we have a couple of helper functions here. We have a helper function which checks whether or not the AI can attack the enemy. And then we have an end state. So this function gets called when the state is exited. So, and all it does here is that we basically want to stop the weapon from firing. So if the AI stops attacking, he should stop firing his weapon. So let's check out the can attack enemy. So first thing we do here is we check whether the pawn is still valid. We check if the current enemy is still valid. We then check if the AI is within range of its weapon. So we go to assault weapon, and then we grab the range of the weapon, get fire mode range. So let's just check that function out. So why does it need a 0? So basically we're grabbing a fire mode, and it's just checking the fire mode num value against the array, and then we get range from the fire mode. And if we check that, so get range, that has a default value of 16,384. So maybe the other ones have different values. So this returns the projectile's approximate distance travel based on its lifespan. And for a trace, we return the trace range value. So the AI now knows how far it can shoot, and it just checks, am I within distance? And if I'm not, return false. We can also check whether the AI is actually pointing at the enemy, so that the AI isn't, pointing in the opposite direction. So again, we use a dot product, check whether the pawn is facing towards an actor, and we check it within the get attack angle. So that is using a very similar type. So it just goes through to the fire mode, get attack angle, and the fire mode just returns the attack angle. So basically, if the weapon needs to be more precise, then the attack angle needs to be closer to 1. But if the weapon doesn't need so much precision, it can be closer to 0. So here we can see the default value for attack angle is 0.87. Okay, so the last thing we check is whether or not the AI actually has line of sight. So we do a quick trace, and if the hit actor does not equal to the current enemy, then we return false. So basically, if the AI, when he shoots his weapon, if he hits someone else that isn't my current enemy, then he probably shouldn't fire his weapon, because there might be a friendly AI in front of this AI. So otherwise, if we can do all of those, if the current enemy is valid, if my pawn is valid, if the enemy AI or the current enemy is within range of the weapon, if I'm pointing at the current enemy, and if I have a clear line of sight to the enemy, then I can shoot my weapon. So that's what that function is doing. So we have a very similar setup in the begin. Essentially, if the pawn is, we check if the pawn is still valid. We go to the dead state if it's not. We check if the current enemy is still valid. If it's not, we go to the end, which breaks out and goes out of the state. We then check whether or not the pawn is inside the walking physics state. And again, we set the movement physics and we set be precise destination to false. We then actually use the logic that we've built up earlier. So the first thing we do is we check, can we attack the enemy? So if we can't attack the enemy, then and I'm still firing my weapon, I want to stop firing the weapon because otherwise I'm just wasting ammo. So if I can fire at the enemy, I'm going to stop movement. And if I'm not firing my weapon at the moment, I'm going to start firing my weapon. So you may want to advance the AI a little bit to keep them moving as they're firing at you. For now, I'll leave this to an exercise to you. So you can probably add some extra states in here. You could possibly remove this, and inside move direct or inside move via pathing, you can say, okay, so if I'm not dodging the character, or if the enemy is attacking me and shooting me, maybe I need to perform some evasive maneuvers and things like that. So okay, so if we can't attack the enemy, it goes down to here, but regardless, we go down to move direct. And the first thing we do is ensure that we have a current enemy. So if the current enemy does not equal none, we set the destination position to the current enemy location. We then check whether we can directly reach that destination or not. So we use, so if we can, we just use be precise destination equals to true. And again, we loop back to can I attack my enemy? So what happens now is that the enemy will continue to advance to the enemy AI and just checks, can I attack them? One thing I've noticed is that this should probably have a sleep and go back to that if we really want to stop the character from moving and advancing. So I'm just going to add that in now. So just using sort of a flow as we read through and as we sort of examine what is the AI wanting to do, we can easily pick up on small mistakes like this. Okay, so if we can't directly reach the enemy, the current enemy, we want to generate a path to it. And again here, I've made a mistake here. So this should be current enemy dot location. So we generate a path to the current enemy location. Pawn.collect, which so we want to get there within this collision radius. And we want to grab the next move location if we could generate a path there. So I'm going to add a if none check, like so, to make sure we don't use that value accidentally. So to make sure we don't get access none, I should say. So if we generate a path, we grab the next move location, like we did in the moving state. We then set the destination position. We then set the focal point so that we look at that destination position, and we set pretty precise destination, so it'll route around, and then we loop back to check, can we shoot the enemy or not. So we should probably loop this back to begin because we want to continue checking the validity of this state, and that's the same with this here. Okay, so those are those two states discussed. So using all of that information, let's actually examine how the pawn behaves. So let's start up a game with some AI in it. But before we do that, the more I thought about this, the more I really want to change this. So I'm actually going to move this up into these things here because we want the final destination to be where we want the actual AI to go. So I'm going to add these here. Okay, and I'll do the same thing for the attacking state. It's probably fine. Okay, so I'm going to give that a quick compile, and we're going to test it inside the game. Okay, so to properly test all this, I'll just turn the... Okay, so I'm going to set this. I'm going to slow down the game a bit so we can analyze the game as we're talking. So I'm going to add 3 bots. We can see they're in the game. I've got 1 on my team and 2 on the blue team. So the player doesn't see any enemies and doesn't need any pickups because he's just spawned. So he's running to the task, and we're going to start. And the other AI is doing the same thing. So the enemy AI, is now seeing me. So he's attacking us. He's lost enough health, so he runs to that pickup. And he's completed that task, and so he's lost enough health that he's going to run towards that pickup, and he picks it up. And then he turns around, and he examines whether or not he needs to attack us. But they've got another task, and that AI has now attacked the other person. So I've attacked him, so he's turned around and started attacking me. So now we're reaching the second waypoint. So as you can see, my team AI is running towards that point. And the other AI are now pursuing us. He's lost enough health, so he goes towards that. He's now running away from us because he's trying to reach that other health. So we're going to continue chasing him down. And we killed him. So then they respawn, and then they start engaging us straight away. So even though we've got some really simplistic AI, we can sort of see, yeah, okay, we can sort of see how this game is starting to be a little bit more fun. You know, you can sort of add on top of this AI to do some different things. So he's got some aim error, so he's not aiming at them. So he's aiming kind of randomly. He's a bad shot at long distances. And that sort of introduces some human error. Because otherwise, if the AI is sort of aimbotting you all the time, it's not very much fun. So you can add some extra logic to make sure that if they're running away from you, to make sure that they run away to a safe location, that sort of thing. So yeah, and so the AI is continuing to engage us. So that's a pretty simple overview of the AI. And we'll just exit that now. So you can sort of see how we have this timer function, which basically just analyzes what should I be doing right now. We have some states which basically control some simplistic behaviors. And you could see as I was reading through it, you could sort of see that, I found that there were some potential logic problems here and there, so I just fixed them straight away. And keeping a really simple and linear AI sort of structure makes it so much easier to actually determine how AI should be thinking and whether they should be thinking smart. So in this case, you don't really want a state to say attack nearby enemies while picking up health packs. Because, when you start creating really, really strict states like that, the AI becomes really rigid, and you don't really get a lot of emergent behavior coming out and these sorts of things. By having some pretty granular, some big sort of states where AI is just wanting to move to here, or AI is just currently wanting to attack this person here, you can create some pretty interesting AI. So that's really the main talk about the AI. And some of the key points that you can take home is the general structure that I've set up is basically a looping timer, which has a reasonably small value, and that small value can be adjusted for performance reason, or that small value can also be adjusted for sort of a response time. I then calculate what the AI should be doing within that timer. I then figure out whether what sort of states the AI actually needs. So I sort of figure out the key kind of goals that the AI is going to achieve, and the states achieve those goals directly. So the timer sets what kind of goal, the what to do timer sort of sets what do I want to do, and the states achieve that goal. So those are really the key points to take home. Keep your AI simple, keep the workflow for the logic simple, and as long as you do that, you can probably create some pretty interesting AI. So in this chapter, we're going to discuss how we can use Kismet to change the behavior of AI. And we need to do this because the Kismet already drives how the tasks are assigned to teams. So if we truly want to allow level designers to have full control over how they want to design tasks. So, say for example, they can think up something crazy. That is to say, a team has to reach this destination, but they have to also carry with them 2 bombs or something, or maybe 3 technicians or 3 techs have to reach this area, or they have to go here to pick this thing up and then deliver it to here, or they have to destroy this thing. So basically, we want to really allow them to really use their imagination to create whatever they want. And that's really the purpose of Kismet in the first place, right? Okay, so in the other chapter where we briefly discussed about the AI, we skipped over a section of the what to do timer function, and that was specifically how to handle tasks. So we're going to go through it. It's a reasonably difficult thing to understand, so I'll try to present it in in the simplest way I can. Okay, so the first thing we want to do is we want to grab the team that the AI is on. So we grab the player replication info and we pull out the assault team info from that replication, from the replication info team reference. So now that we have the assault team info, we can grab the list of task infos. So if you recall from DVD number 2, the task infos register themselves with teams. And we can find that. We can look that up. So the register task inserts itself inside the team. Okay, so now the AI has a list of tasks that it can do. So the next thing we do is we iterate through the tasks, as we do here. We check whether or not the task has been completed. If it's been completed, then we don't need to worry about it because either another AI or this AI or a player has already done that. So we skip past it. We then evaluate. We want to evaluate tasks which haven't been completed yet. So the way we do that is we want to call a Kismet event. And the way we can do that inside script is the first thing we need to do is we grab the game sequence, which is basically like the root game sequence inside the level. We then find Kismet sequence objects by class, and in this case we're finding this particular class called assault sec event evaluate task. We then do true for a recursive search, and we store all the objects that we find inside sequence objects. So if this thing finds a whole bunch of Kismet nodes called assault sec event evaluate task, it's going to shove them into the sequence objects array. So we then iterate through this array. We then double check. We then first thing we do is we typecast the sequence object inside the sequence objects array as a assault sec event evaluate task. If the typecast has succeeded, the first thing we do is we copy the link variables to the member variables. So basically what we're doing here is we're pushing the values from the link variables to the member variables. So I'll just start up Unreal Editor to demonstrate what that actually does. Right, so here's an example of a task. So we've got these two things here that's connected to this evaluate task control node, or Kismet node, sorry. And so basically we want to copy this value and this value into the Kismet variables inside UnrealScript. So basically we then check whether or not this linked task info is the task in question. So we only want to evaluate the task Kismet nodes connected to the task that we're actually currently evaluating. So from there we copy the controller over, because as you can see here in the Kismet, controller is outputted. It needs to know which controller we're dealing with. So we copy that out, and then we populate the linked variable values. So this basically says that inside the script, we copy the value of the controller into this node here, and then we ask that evaluate task to activate itself. So essentially what we're doing from here is that this has now become activated, and it triggers whatever comes after that. So far so good. So once it does that, it breaks out. Okay, that's great. So let's have a look at the assault sec event evaluate task class. So we have it here. So we can see that it just has a linked task info, and this value is usually set within Kismet itself. And we have the controller, and this value is set from script to Kismet. Okay, so now we have the AI controllers asking Kismet to activate a Kismet event, and it's copying some values into Kismet. So now Kismet has control over this controller. Kismet can do something, and essentially what we have is a bunch of smaller Kismet actions which then control the attached controllers. So that's a nice, pretty simple setup. So we have one here called assault sec act move to location. So this is basically a Kismet sequence action which will inform the AI controller to move to a location. So essentially what level designers can do in this case is, if they want the AI to move to somewhere, then they just basically use a node like this. So they can also add some conditions to, say that, if you have this weapon, then you actually want to position yourself here, or if you're carrying this kind of inventory, you want to position yourself here. If you're this kind of class, then you want to be running down there, so on and so on. So the possibilities are kind of endless at this point. So let's examine this and let's see how this works. So when it is activated, first we copy the link variables to the member variables, and again, basically what that's doing is that inside here we've got a bunch of variables that are linked via Kismet, and we want to copy the values of these into this Kismet node, or into these variables up here. So then we typecast the controller reference to an Assault AI controller. We then grab the actual location, and this is where we give the level designers a choice. They can either define a vector location, or they can define an actor location. So an actor location is usually easier for level designers because they can place something down like a trigger or a note or something along those lines and just say, okay, just move to wherever this actor is. A vector location can be a little bit more precise, and that may be easier for some level designers as well, if they don't feel like placing down another actor somewhere or whatever, for whatever reason. Okay, so we grab the actual location. The actor has priority over the vector location. So, because I usually know that from experience, most level designers usually just want to use an actor to define a location. So the first thing we do is we set the Assault AI controller's final destination, like this. We probably should add an access none check here, just in case. Since none of this is going to work without setting that, we add the block like this. We then set the destination position to get the AI to think about trying to run there. And then we set the focal point, so the AI will actually look there. And if the AI isn't in the moving state, then go to the moving state. So precisely from here, this Kismet sequence action is already telling an AI to do something. So it's overriding, well, it's actually, sorry, it's not overriding anything. It's basically a follow-on in Kismet. This is transitioning from UnrealScript to handle a task, and then it's asking Kismet to handle the controller from here on in. So this gives unprecedented power to the level designer to then say, like, okay, I want the AI to move here and here and here. So let's give it a concrete example. In the first task, what I actually have is a task where players have to reach a waypoint for the red and blue teams. So the red team just has to reach waypoint 1. So to reach waypoint 1, the task is a very simple thing to do. So when the AI has to evaluate the task, so as you can see here, if the task, when the AI passes through the list of the evaluate task Kismet event nodes, it then checks whether the task is the one it's trying to do. So that's why we have this linked here. If it is, then it outputs the controller, and essentially we're just telling the AI to move to this trigger here. So let's find where that is. Select trigger 0 in level. Alright, so essentially the red team starts here, and we want the AI to run there, because that's how the AI achieves that goal. So that's really simple. So for the blue team, we set up a similar goal. So for the blue team, they have a task to defend this waypoint, and basically when the blue team AI has to evaluate the task, it then says, oh, okay, I need to move to trigger _7. And that is down there. So basically what we're doing is that when the AI has nothing to do, it tries to do a task, and basically the blue team members will start here and they'll run down, and they'll try to reach here. But of course, as they're running down here, they're going to encounter the red team, so they'll switch to the enemy attacking state, and if they run low on health, then they'll pick up and stuff like that. But the difference is that when the red team actually gets to this area, they can complete this task. However, the blue team can't ever complete this task. this task is only ever completed by the red team, ironically enough, because when the red team reaches that waypoint, the blue team then has to defend the second waypoint. Makes sense, right? So essentially, we've solved the problem where level designers can create this complex task in Kismet, and we've solved the problem of trying to get the AI to respect what that task should actually be about. And because we have this simple setup here, we can add some conditions. So if AI has, if AI is in combat, or so on is on this particular team, or maybe he's got some, maybe you want to do a counter so that AI will send 2 guys there and then 2 other guys here, and so on. You can do all sorts of things that you want as a level designer, and that's really nice actually. So let's examine some of the other ones we've got. So the other one we've got is a assault sec act attack actor. And so basically this Kismet sequence action will allow AI controllers to attack an actor. So level designers here can create a task where maybe the red team has to destroy a generator of some sort. So we go, okay, so how do we do that? So using the same flow, this Kismet sequence action will be activated when the evaluate task Kismet event is activated. We then copy the variables again because we need access to that controller that was pushed out. We then typecast that controller into an assault AI controller. And again, we set the current enemy to the actor. We set the destination position, we set the focal point, and then we tell the AI to go to the attacking state. So that's a pretty nice setup, and we'll just make an example. Right, so we have our test map open. So we'll just check out the Kismet. Right, so there are 2 tasks here. Here's one task. And here's the other task. Now this task here, we just want the AI to reach somewhere, but we'll probably just delete that one. We don't need that one right now. Just set that to 0, so it becomes task 1. So essentially for this task here, what we want the players to do is to destroy this K actor. So we want the AI to destroy this. Or we want basically the red team to destroy this. So we have this evaluate task here, and this is the controller, and we just have an attack actor to this K actor. So essentially what's going to happen is that the controller, when they get asked to evaluate this task, they're just going to get told, okay, I want you to attack this K actor. So let's see it in action. So I'm just going to fly up here so that we can see the bot in action. Just going to slow it down so we can make some commentary on it. So if I go add bots 1, we can see the bot has spawned. He's running towards, he's using pathfinding to reach towards the task. And as soon as he's able to attack it, he starts shooting it. And there we go. The AI has actually successfully achieved this task. So this is a pretty interesting setup because now we've successfully crossed that gap of trying to resolve the problem of the AI trying to figure out what the level designer has in mind. And by using all the tools available to us, such as Kismet in this case, we can really expand upon the AI in lots of really interesting ways, because then we can start saying, well, maybe some of the AI should be cut out and be put into Kismet so that for different levels, the AI can act really differently. For example, if the level is really windy and quite serpentiney, then maybe the AI switches to, maybe the AI knows about this, and so they'll tend to pick classes which have less splash damage. And that can be determined because the level designer knows what kind of map he or she is building, so they can say to the AI, this is the kind of map it is, this is some of the weapons we suggest. And the same could go for things such as maybe the AI will try to jump a lot more in different types of maps, or crouch a lot more, or be a bit more tactical than in a brute force manner, this and that. So I think using Kismet in this fashion, for some people, especially some other programmers, they may see it as a bad thing, because then you're splitting up the work between programmers, the level designers, and game designers, and so forth, and it can become a really convoluted mess. But I think it's really about who needs to actually do that job. So if we're already letting level designers design what kind of tasks to do, then surely the level designers should be designing how the AI should actually accomplish those goals. And I think when looking at it from that perspective, it makes a lot more sense to design a system exactly like this. So it looks like we have one more sequence action here that I've created, and that is to clear current enemy. And basically, when the AI has destroyed something, it may not automatically know how to actually remove that from its current enemy. Because in this case, in the example that we saw, when the AI had destroyed that container, it had no way of knowing whether that container was dead or not, because the object still exists in the map and so forth. So I have this other Kismet action here, which essentially says that if any assault AI controllers have the current enemy linked to the actor that's linked to this Kismet node, then clear it, which is what I've done down here. So when the task has been completed, because the K actor was destroyed, we then clear all current enemies for all controllers that are currently targeting this K actor, so that they can continue on and do something else. Okay, and that really just about covers exactly how I approached this problem and my thought patterns on deciding what was the best way I should tackle this. This was genuinely the first idea that I tried, and it was successful. So I guess that's a good thing. But I guess one of the take-home messages that I really want to impress upon you is that when you come up across a difficult problem like this, the best thing to do is probably to lay out all the available tools that you have, and then to say, like, okay, I can do this inside UnrealScript, I can do this inside Kismet, perhaps I can do this as a mixture of both, maybe I want to use archetypes, maybe I want to do this or that. Once you lay out all your tools and what you have available to you, it becomes much easier to decide exactly how you want to solve this problem. So in this last chapter, I just wanted to tidy up some of the last little bits of changes that I've made to the Assault game. So in the previous DVD, in DVD number 2, I talked a little bit about handling friendly fire. So if I'm on the blue team and I happen to shoot a teammate, then no damage should be applied to the teammate. And I implemented this by checking the pawn and checking whether they were on the same teams, and if they were, I reduced the damage down to 0. Now, there were some obvious bugs with this and some obvious problems with this as well. The first bug that arose was that if you were to shoot the rocket launcher right near to you, so, say you were up to, right against the wall and you shot the rocket launcher, it wouldn't damage you because the projectile, when it exploded, would detect that you were on the same team as yourself, and thus it would reduce the damage down to 0. Now, this is obviously not really good behavior, because this sort of encourages a suicide-like gameplay, and we don't want to do that. So that was really the bug with that. The major problem with this sort of design, or this code design, is really that once we start having to add different types of projectiles or different types of trace weapon fire modes and so forth, we would have to duplicate this code over and over and over again. And that's obviously not a really flexible way of doing things. So for DVD number 3, before I really added any new things to it, I wanted to really review the system. And one of the things I found was that in the take damage function inside pawn, there is actually a hook to the game info which allows it to reduce the damage. Now, this hook is really useful to us because then we allow the game info to actually adjust how much damage is applied. And it's being passed several parameters that can all be useful to determine whether or not damage should be applied or not. And of course this extends to, this is where we can actually check in a single place whether damage should be applied or not. Now, with this hook, this is only in the pawn take damage, and if you recall in DVD number 2, we had to override sort of the default take damage behavior inside the cyborg pawn. So inside the cyborg pawn, I also added a hook to allow the game info to reduce the damage when it was just taking down the shields. So with that in mind, we were able to override this function in our custom game info. And as you can see here, this is where I actually check, first of all, whether or not the injured pawn is the same as if it was a self-shot, or you shot a rocket right in front of your face, then of course I'd return straight away, because then it should damage you. I then check whether the injured pawn is on the same player, and if it is, then I reduce the damage down to 0, because I don't want you to be able to hit team members. However, this is a really prime place where you could probably add a config variable which allows you to say whether friendly fire is a percentage. So on the config you can set, the user can set that from 0 to 1, and that can sort of scale the friendly fire. I also added in the older rules, which was that if it was in a physics volume which was defined as a neutral zone, or if the injured pawn was in God mode, then damage would be set to 0. And then we allow mutators to modify the damage as well. So now we have this friendly fire code in one place, and it's a much better workflow it's a better code flow, so that when you decide to add new fire modes, or different projectiles that do different things, or anything like that, you don't have to worry about having to re-add that code in as well. So I've been browsing a lot with the threads on the UDK forums, and as well as on the Eat3D threads as well, and a few of you have asked some questions, so keep those questions coming. And a few of you have also asked for my contact details as well. So you can always email me at james.tan@digitalconfectioners.com, or you can send me a message or post a thread on the UDK forums, and I'll be happy to answer your questions about the DVD series. And that's it for this DVD series. Thank you.